Spanning an awe-inspiring 93 billion light-years in diameter, the observable universe is a colossal cosmic bubble, a vast expanse that holds everything we can see or detect from Earth. It encompasses every star, planet, galaxy, and even the faintest speck of cosmic dust, all of which light has traveled across since the birth of the universe, approximately 13.8 billion years ago. This seemingly unfathomable stretch of space is just a fraction of the entire universe, with a scale so vast that it dwarfs our comprehension. But what lies beyond the observable universe? The true mystery of space lies in the uncharted territories, areas that are not only invisible, but beyond our current detection capabilities. Using the speed of light as a cosmic ruler, scientists have established how far we can see as light travels at a fixed speed of 300,000 kilometers per second. We can only observe as far as light has had the time to reach us, and that distance marks the boundaries of the observable universe. The light we see now has been traveling through space for billions of years, offering us glimpses of distant galaxies and stars, but it is merely a small snapshot of a far grander cosmos. This notion invites curiosity, pushing us to wonder about the mysteries hidden beyond the cosmic horizon. Is there more out there? And if so, what could it be? Now, the unobservable universe, a realm that stretches beyond the limits of what we can measure or detect, emerges as a place that defies our understanding. While the observable universe extends roughly 93 billion light-years in all directions, scientists believe that the unobservable universe is far larger, perhaps even infinite. This belief is rooted in the inflation theory, which proposes that moments after the Big Bang, the universe expanded at an incredible rate, faster than the speed of light itself. This rapid expansion could have created a universe that continues to grow far beyond our detection limits, forming vast regions filled with countless other observable universes, each brimming with galaxies, stars, and planets. Though we cannot yet grasp the true scale of the unobservable universe, it captivates our imagination, leaving us to marvel at its vastness and potential. How many galaxies lie hidden in this unexplored expanse? Could other civilizations, other worlds, exist in parallel universes that are just beyond our reach? These are questions that fuel scientific inquiry, sparking a fascination with what lies beyond the limits of human perception. At the heart of the cosmos lies the universe's fundamental structure, elegantly simple yet profoundly complex. It is composed of three primary components: matter, and dark energy. Matter, the familiar substance that forms stars, planets, and galaxies, accounts for only about 5% of the universe. This visible matter includes everything we can see: planets, asteroids, and even the smallest particles that make up the stars. But beyond this visible matter, the true mysteries of the cosmos emerge. Dark matter, which makes up roughly 27% of the universe, remains invisible. It cannot be seen, nor can it be detected by conventional means. Yet we know it exists because of its gravitational influence on visible matter. It's this unseen force that acts like a cosmic scaffold, shaping the structure of galaxies and holding them together. But perhaps the most enigmatic force in the universe is dark energy, which makes up about 68% of the cosmos. Dark energy is responsible for the accelerated expansion of the universe, pushing galaxies apart and defying the gravitational pull of matter. Together, these three components, matter, and dark energy, form the very fabric of the universe. They are the building blocks that govern the cosmos, from the smallest subatomic particles to the grandest galaxies. Yet, even as we explore these elements, much remains unknown. How do dark matter and dark energy work in tandem to shape the universe? How does the balance between these forces create the universe we observe? To measure the unfathomable vastness of space, astronomers have devised ingenious methods. The light year, a measure of distance equal to the distance light travels in 1 year, about 9 trillion kilometers, is one of the most common units for measuring cosmic distances. For nearer objects within our own galaxy, astronomers use the method of parallax, measuring the shift in an object's position as observed from two different points in Earth's orbit. However, as we peer deeper into space, the methods grow more complex. For distant stars and galaxies, astronomers rely on standard candles, objects like Cepheid variable stars whose intrinsic brightness is well understood. By observing how bright these objects appear, astronomers can estimate their distance. But when it comes to measuring the most distant objects, galaxies far beyond our reach, the redshift method comes into play. As the universe expands, light from distant galaxies is stretched to longer, redder wavelengths. By measuring this redshift, scientists can determine the distance and speed at which these galaxies are moving away from us, providing essential clues to the universe's expansion. The discovery of dark energy, a mysterious force that permeates all of space, has profoundly changed our understanding of the cosmos. Dark energy makes up about 68% of the universe's total energy, and it is responsible for the accelerated expansion of the universe. Unlike gravity, which pulls objects together, dark energy pushes them apart. Its existence was first suggested in the late 1990s, based on studies of distant supernovae, which revealed that galaxies were moving away from one another at an increasing rate. Dark energy does not emit or absorb light, making it incredibly difficult to detect directly. Instead, its presence is inferred from its effects on the structure and expansion of the universe. Understanding dark energy is crucial, not just for comprehending the universe's current state, but for predicting its future. What role does dark energy play in the eventual fate of the universe? Will it continue to push galaxies apart forever, leading to an ever-expanding universe? Or is there more to dark energy's nature that we have yet to uncover? These questions, and the quest to understand dark energy, continue to drive the search for answers in the mysterious depths of the cosmos. The universe is far more than a collection of stars and galaxies. It is a dynamic, ever-evolving entity, with forces at play that we are only beginning to understand. As we look to the future, one thing is certain: the journey to unlock the secrets of the cosmos has only just begun. The mysteries of the observable and unobservable universe continue to beckon us, challenging our perceptions and pushing the boundaries of scientific inquiry, but also to predict the ultimate fate of the universe. Will it expand forever, or will dark energy evolve over time, leading to a different cosmic end? The quest to unravel the mysterious nature of dark energy continues to both challenge and inspire scientists across the globe. This enigmatic force, which drives the accelerated expansion of the universe, holds the key to understanding not only our cosmic destiny, but the fundamental workings of the universe itself. Dark matter, an invisible yet profoundly influential component of the universe, plays a crucial role in its structure and evolution, comprising about 27% of the universe's total mass energy content. Although dark matter cannot be seen because it neither emits, absorbs, nor reflects light, it exerts a powerful gravitational influence, detectable only through its effects on visible matter. Without dark matter, the behaviors observed in galaxies and galaxy clusters would be inexplicable, as the gravitational pull from visible matter alone cannot account for their movements. Dark matter acts as a cosmic glue, holding galaxies together and preventing them from flying apart as they spin. It provides the necessary scaffolding for the universe's large-scale structure, with galaxies and clusters of galaxies forming along the densest regions of dark matter. This invisible framework is fundamental in shaping the cosmos. Without it, the gravitational forces generated by visible matter alone would be too weak to form the galaxies and vast structures we observe today. By influencing the distribution and movement of galaxies, dark matter plays a foundational role in the intricate web of the universe, weaving together the cosmos into something truly awe-inspiring. Galaxies, those majestic cosmic structures that host stars, planets, gas, and dust, have their origins in the primordial fluctuations of the universe's density shortly after the Big Bang. These tiny variations, almost imperceptible at first, serve as the seeds from which galaxies would later sprout. Over millions of years, these fluctuations gradually drew in surrounding matter, including dark matter, creating the gravitational pull that would give rise to the first stars. As these stars formed, they began to release energy and heavier elements into their surroundings, catalyzing the birth of more stars and eventually leading to the formation of entire galaxies. As time marches on, galaxies evolve in complex and often dramatic ways. They can grow by accreting gas from the surrounding intergalactic medium, transforming this gas into new stars. Some galaxies experience explosive growth during mergers or interactions with other galaxies. These cosmic collisions can drastically alter their shapes, star formation rates, and overall structure. Spiral galaxies, for example, might transform into elliptical galaxies due to these violent encounters, while isolated galaxies can continue to form stars at a steady pace, or once their gas is exhausted, they may turn into dormant realms filled with older stars. The life cycle of a galaxy is a testament to the dynamic and ever-changing nature of the universe, constantly shaped by gravity, the interstellar medium, and the intricate interplay between galaxies themselves. Among the most profound discoveries in cosmology is the cosmic microwave background, CMB, radiation, a faint afterglow of the Big Bang that permeates all of space. This relic radiation offers a unique window into the early universe, revealing insights into its infancy. Detected accidentally in 1965, the CMB serves as a crucial clue in understanding the origins of the universe, providing evidence of the momentous event that began it all, approximately 13.8 billion years ago. The CMB is not just a remnant of the past, but also a vital tool for cosmologists, helping to unlock the mysteries of our universe's earliest moments. But its significance was quickly realized as it provided the most compelling evidence for the Big Bang theory. This relic radiation, now cooled to just 2.7 degrees above absolute zero, bears the imprints of the young universe, about 380,000 years after its genesis. It was a time when particles and light finally decoupled, allowing light to travel freely. The minute fluctuations in the cosmic microwave background, CMB, temperature reveal the early distribution of matter, serving as the seeds for the formation of galaxies and the large-scale structure of the universe. Moreover, the CMB has been instrumental in shaping our understanding of the universe's composition, age, and rate of expansion. Through detailed observations of the CMB by satellites such as COBE, WMAP, and Planck, cosmologists have refined the standard model of cosmology. The CMB not only underscores the universe's dynamic evolution from a hot, dense state, but continues to guide our inquiries into the cosmos's deepest mysteries, such as the nature of dark matter and dark energy. As we peer deeper into the fabric of the universe, the ultimate fate of all that exists remains a captivating and enigmatic subject. Scientists and stargazers alike have speculated on the universe's end, with three prevailing theories: the Big Freeze, the Big Rip, and the Big Crunch. The Big Freeze, considered the most likely scenario based on current understanding, suggests that the universe will continue expanding at an accelerated pace, driven by dark energy. Over trillions of years, galaxies will drift apart, stars will burn out, and black holes will eventually evaporate. What remains will be a cold, dark, and desolate expanse with temperatures approaching absolute zero. In stark contrast, the Big Rip theory proposes that dark energy's influence could become so dominant that it tears apart not only galaxies but stars, planets, and even atoms themselves, ripping the very fabric of space-time. This scenario would mark an unimaginable destruction of the cosmos. The Big Crunch presents a third possibility: a gravitationally dominated universe where the expansion eventually halts and reverses, collapsing back into a singular, infinitely dense point. This could set the stage for another Big Bang, starting the cycle anew. Each of these theories depends on deep, unresolved questions about the nature of dark energy, dark matter, and the fundamental forces of the universe. As our understanding evolves, so too will our insights into the ultimate destiny of the universe itself. Meanwhile, the idea of a multiverse, once confined to the realm of science fiction, has moved into the realm of serious theoretical consideration in physics. The multiverse suggests that our universe is just one of potentially countless others within a grander cosmic expanse. Among the leading theories about the multiverse, several stand out due to their implications and the scientific frameworks that support them. The quantum multiverse, which stems from the many worlds interpretation of quantum mechanics, proposes that every quantum event leads to the splitting of the universe, creating an infinite number of parallel realities. Each of these universes diverges based on the different outcomes of these quantum decisions. Another fascinating theory is the cosmic inflationary multiverse, which extends from the theory of cosmic inflation. It suggests that during the early universe's rapid expansion, different regions stopped inflating at different times, leading to bubble-like pocket universes within a much larger space. Each of these pockets could possess different physical laws and constants. Lastly, the multiverse could also emerge from the mathematics of string theory, which posits that extra dimensions exist. These dimensions can be configured in numerous ways, each configuration leading to a different set of physical laws, resulting in a vast landscape of universes with diverse properties. Finally, the parallel brains concept within string theory and M theory presents a compelling vision. It suggests that our three-dimensional universe exists on a brain, a multi-dimensional object within a higher dimensional space. Other brains floating in this higher dimensional space could host their own universes that each potentially very similar to our own, but with slight variations in their fundamental properties. In exploring these theories, we are left to ponder the nature of existence itself. As we continue to push the boundaries of science and technology, we may one day find the answers to these profound questions, shedding light on the mysteries of the universe, the multiverse, and our place in the cosmic order. Theories about non-intersecting worlds, though speculative without direct evidence, open vast avenues for understanding our place in the cosmos. These theories suggest that our universe may not be the only one, but rather one of an unimaginable number of universes existing within a much larger structure, the multiverse. This tantalizing idea raises profound questions about the nature of reality and our existence within it, offering a glimpse into a far grander and more complex reality than previously conceived. Among the most awe-inspiring discoveries in modern astronomy is the revelation of IC 1101, the largest known galaxy as of current findings. Located in the heart of the Abell 2029 galaxy cluster, IC 1101 is positioned approximately 1 billion light-years away from Earth. This supergiant elliptical galaxy stretches an astonishing 4 million light-years in diameter. To put its vast size into perspective, consider this. The Milky Way, our home galaxy, spans a mere 100,000 light-years, meaning IC 1101 is nearly 40 times larger. Discovered by British astronomer Frederick William Herschel in 1790, IC 1101 is thought to have formed through the merger of many smaller galaxies over billions of years. The sheer scale of IC 1101 potentially hosts trillions of stars, far surpassing the estimated 200 to 400 billion stars in our own Milky Way. The galaxy's enormous size provides a striking glimpse into the true scale of cosmic structures and the processes that give rise to such mammoth formations. These findings force us to reconsider the boundaries of our understanding of the universe and our place within it. At the heart of most large galaxies lies a supermassive black hole, and these cosmic giants are thought to play a critical role in the formation and evolution of galaxies. Supermassive black holes, which can range from millions to billions of times the mass of our Sun, exert a powerful influence on their host galaxies despite their relatively small size. One of the ways these black holes impact galaxy formation is by regulating star formation. As material spirals into a black hole, it heats up and emits intense radiation, creating jets of particles that travel at nearly the speed of light. This phenomenon, known as a quasar or active galactic nucleus, is incredibly energetic. These jets of radiation and particles can heat up surrounding gas or even expel it from the galaxy's central regions. The result is that the gas is prevented from cooling and collapsing, making it impossible for new stars to form. This process is believed to be a self-regulating mechanism that limits the number of large, bright galaxies in the universe. If star formation were allowed to continue unchecked, the number of such galaxies would be far greater than what we observe. The relationship between the mass of a supermassive black hole and the properties of its host galaxy's bulge, such as the bulge's mass and the speed of stars within it, suggests a deep connection between black holes and galaxy formation. While the exact nature of this connection remains an active area of research, it is likely that complex feedback processes are at play, where the growth of black holes and the formation of galaxies influence one another. In another fascinating corner of the universe lies the Great Attractor, a gravitational anomaly located approximately 250 million light-years from the Milky Way within the Norma cluster. This mysterious region of space exhibits a gravitational pull so immense that it affects the motion of galaxies across vast distances, hundreds of millions of light years away, including our own Milky Way galaxy. Despite being obscured by the plane of our galaxy, which makes direct observation difficult, the influence of the Great Attractor is detectable through the peculiar velocities of galaxies. These galaxies are moving in strange patterns, influenced by a gravitational pull that is not solely due to the expansion of the universe. What makes the Great Attractor particularly intriguing is its role in revealing the large-scale structure of the universe. Galaxies, including the Milky Way and its neighboring galaxies, are not only moving away from one another due to the expansion of the universe, they are also being pulled toward regions of higher gravitational attraction, like the Great Attractor. This discovery challenges our understanding of the cosmic fabric and forces us to reconsider the hidden forces shaping the universe's evolution. The Great Attractor is not just a fascinating anomaly. It is a key piece of the puzzle in understanding the grand cosmic forces at play. This massive structure is believed to lie at the very heart of the Lanaka supercluster, an immense collection of galaxies and galaxy clusters that includes our own. The Great Attractor, as it's known, extends its influence far beyond merely altering the trajectories of local galaxies. Its impact provides essential insights into the distribution of both visible and dark matter across the universe. This in turn aids astrophysicists in understanding the overall structure of the universe and the complex dynamics that govern its vast expanse. The Great Attractor reveals forces that sculpt the cosmos on its grandest scales. Galaxies can collide, and these cosmic encounters are far more frequent than one might think. When galaxies draw near, their mutual gravitational pull can set them on a collision course, initiating a dramatic merger. This process can take hundreds of millions of years to complete. Despite the countless stars within each galaxy, direct collisions between stars are exceedingly rare due to the vast distances between them. Instead, the gravitational forces between colliding galaxies warp and reshape their structures. During these galactic collisions, gas clouds within the galaxies collide violently, creating shock waves that compress the gas and trigger new waves of star formation. This phenomenon lights up the galaxies with the birth of new stars, a period known as a starburst. The collision can also feed the supermassive black holes at the galaxy's centers, leading to the formation of active galactic nuclei, AGN, or quasars, which emit vast amounts of energy. Over time, the two galaxies merge, combining their stars, gas, and dark matter into a single larger galaxy. The resulting shape may be radically different from the original galaxies, often transforming into an elliptical galaxy, even if the progenitors were initially spiral-shaped. One of the most famous examples of galactic collisions is the ongoing interaction between the Andromeda Galaxy M31 and the Milky Way. In approximately 4 billion years, these two galaxies are expected to collide, merging into a new, larger entity, sometimes referred to as Mila in popular science discussions. Through these colossal encounters, galaxies evolve, change shape, and sometimes even give birth to entirely new types of galaxies, showcasing the dynamic, ever-changing nature of the universe. Quasars, or quasi-stellar objects, are among the most luminous, powerful, and energetic phenomena in the universe. Found in the centers of galaxies, they are powered by supermassive black holes. As matter spirals into these black holes, it heats up and emits enormous amounts of light and other forms of radiation. This intense energy makes quasars visible, even at the very edges of the observable universe. The importance of quasars is profound. They serve as cosmic lighthouses, illuminating the dark epochs of the early universe. By studying quasars, scientists can gain crucial insights into the formation and evolution of galaxies, providing a window into the universe's past when it was only a fraction of its current age. The Boat's void, discovered in 1981, is another fascinating cosmic feature. This vast expanse of space is strikingly empty, spanning over 300 million light-years in diameter. It is one of the largest known voids in the universe, offering a glimpse into the vast, unexplored regions of space where very little matter exists. Studying such voids helps scientists understand the distribution of galaxies and the mysterious dark matter that permeates the cosmos. These cosmic phenomena illustrate not only the awe-inspiring scale of the universe, but also the profound forces that shape it, from galactic collisions to the powerful energy of quasars and the enigmatic voids that populate the vast expanse. As we continue to observe and explore these phenomena, we uncover deeper insights into the nature of the universe and our place within it. But they are also key to understanding the violent energetic processes that drive the evolution of galaxies. When galaxies collide or pass close to each other, the intense gravitational forces cause massive disruptions. Gas clouds are compressed, triggering a sudden and intense burst of star formation. These galaxies are alive with activity, creating stars at a pace that dwarfs the Milky Way's usual rate. As a result, they often appear brighter, with their star formation regions glowing with vivid, radiant light. Despite their explosive nature, starburst galaxies are not always stable. Over time, the burst of star creation exhausts the available gas, causing the rate of new stars to slow down. This means that starburst galaxies tend to burn out after a relatively short period, astronomically speaking. Still, this brief period of high-intensity star formation leaves an indelible mark on the galaxy's evolution, influencing its size, shape, and stellar content for billions of years. By studying these galaxies, scientists can unlock the secrets of galaxy formation, especially in the context of extreme environments and cosmic interactions. The role of cosmic voids and their effects on galaxy formation and evolution cannot be overstated. In contrast to the dense clusters of galaxies found in other parts of the universe, these empty expanses challenge our understanding of how matter and galaxies are distributed. The study of voids like the Boots void is fundamental to our comprehension of the large-scale structure of the universe. This vast emptiness offers a unique laboratory for testing models of cosmic evolution, from the formation of galaxies to the behavior of dark energy and dark matter. Scientists continue to explore the possibility that these voids could hold key information about the very nature of the universe's expansion and the forces that govern it. Could these vast cosmic deserts be areas where matter simply couldn't form due to early cosmic conditions? Or are they simply the result of gravitational forces over vast periods of time, with the cosmic structure slowly pulling matter together into massive filaments and leaving behind regions devoid of galaxies? Whatever the explanation, these regions have become crucial to understanding the universe on its largest scales. The study of voids, galaxy filaments, rogue galaxies, and starburst systems is pushing the boundaries of cosmology, helping to shape our understanding of the cosmos and our place within it. These cosmic phenomena are not just curiosities, they are essential pieces of the puzzle, each providing invaluable insights into the birth, growth, and fate of the universe. As technology continues to advance, the exploration of these mysterious phenomena will only deepen. The tools at astronomers' disposal, from powerful space telescopes to ground-based observatories, are unlocking new chapters in the story of the cosmos. With each discovery, we come closer to answering some of the most profound questions in science. How did the universe come to be? What will its future hold? And perhaps most intriguingly, are we alone in the vast, infinite expanse of space? Through these explorations, we are not just looking at distant galaxies and phenomena, we are peering into the very fabric of existence itself. And as we gaze outward into the void, we begin to understand that even in the emptiness, there is something profoundly important to be discovered. The more we learn, the more we realize that the universe is far more complex and mysterious than we ever imagined, challenging our understanding of space, time, and the fundamental forces that shape everything around us, but also serve as critical laboratories for understanding stellar formation and evolution. The intense bursts of star formation that occur within galaxies are brief in the grand scheme of cosmic time, lasting only a few tens of millions of years. Despite their short lifespan, these explosive events can have profound impacts on the galaxy's future, exhausting vast amounts of gas, seeding the interstellar medium with heavy elements produced by supernova, and shaping the formation of subsequent generations of stars. Among the vast array of stars that populate the universe, a few types stand out due to their extraordinary and often baffling characteristics. Magnetars, a type of neutron star, are one such example. With magnetic fields trillions of times stronger than Earth's, these stars possess the most intense magnetic forces known in the universe. The sheer power of these magnetic fields can trigger spectacular bursts of gamma rays and X-ray visible across great distances. Magnetars are not just a curiosity, they offer a glimpse into the extreme environments that govern the most violent stellar events. Another incredibly rare and theoretical star is the Thorne-Zitkow object, TZ. This bizarre hybrid star is hypothesized to form when a neutron star becomes engulfed by a giant or supergiant star. The resulting object challenges our understanding of stellar evolution, blurring the line between different types of celestial bodies. If discovered, a TZ object could rewrite much of what we know about star formation and the complex relationships between stars in binary systems. Then there are the Wolf-Rayet stars, massive celestial bodies in a brief, violent phase of their life cycle. These stars are known for their incredibly strong winds, which blow off their outer layers, exposing their hot and bright cores. The rarity of these stars, combined with the stunning nebulae they produce, makes them one of the most extraordinary phenomena in the cosmos. Their fleeting existence plays a critical role in enriching the universe with elements necessary for life and providing insight into the final stages of stellar evolution. Lastly, pulsars, highly magnetized, rotating neutron stars, emit regular beams of electromagnetic radiation which have earned them the nickname cosmic lighthouses. Their precise, rhythmic pulses make them valuable tools for studying fundamental physics, including testing theories of general relativity. Their regularity is so precise that pulsars are used as cosmic timekeepers, offering a unique window into the forces that govern the universe. These stars, among others, underscore the breathtaking diversity of the cosmos, offering us fascinating windows into the extreme conditions and processes that dictate the life and death of stars. A star's journey to becoming a supernova occurs through one of two principal processes, both leading to a spectacular explosion that marks the end of its life cycle. The first process involves a massive star, at least 8 times the mass of our Sun. In the final stages of its life, this star exhausts its nuclear fuel, losing the ability to generate the necessary outward pressure to counterbalance its own gravitational pull. As a result, the core collapses in a fraction of a second, and the outer layers of the star explode in a cataclysmic core collapse supernova. The second process occurs in a binary star system, where one of the stars is a white dwarf. Over time, the white dwarf accumulates matter from its companion star, gradually increasing in mass until it reaches a critical limit known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. Beyond this threshold, the white dwarf can no longer support the extra weight, leading to a runaway nuclear fusion reaction, resulting in a thermonuclear supernova. Both types of supernovae play crucial roles in the cosmos. They disperse heavy elements such as iron, nickel, and oxygen into the interstellar medium, which are essential for the formation of planets and life. The shock waves from these explosions also influence the formation and evolution of new stars, further shaping the structure of the universe. Magnetars, a distinct class of new stars, are characterized by their extraordinarily strong magnetic fields, up to 1,000 times more powerful than those of typical neutron stars. Neutron stars, the dense remnants of supernova explosions, are already known for their extreme conditions, including incredibly fast rotation speeds and powerful magnetic fields. However, magnetars take these conditions to extremes, with magnetic fields that can exceed 10 trillion Gauss, far stronger than Earth's magnetic field, which is about half a Gauss. The intense magnetic energy of a magnetar can power spectacular astronomical events, including bursts of X-rays and gamma rays, making them some of the most magnetically intense objects in the universe. This magnetic force is so powerful that it can distort the shape of the magnetar, triggering starquakes that enhance the emission of high-energy radiation. While the exact mechanisms behind the formation of such strong magnetic fields remain a subject of ongoing research, scientists believe they may be linked to the rapid spin of the neutron star and the resulting dynamo effect during its early stages of evolution. Magnetars are not just remarkable for their magnetic fields. Their unique properties set them apart from regular neutron stars and highlight the extreme conditions that can exist in the universe. In conclusion, The universe is home to some of the most fascinating and extreme celestial phenomena. From magnetars to supernovae, these cosmic objects challenge our understanding of the universe and provide us with a deeper insight into the processes that shape the cosmos. As scientists continue to study these enigmatic stars, they offer us a rare glimpse into the violent and awe-inspiring forces that govern stellar life and death, forever expanding the boundaries of our knowledge. But also enigmatic objects of profound study, revealing the intricate behaviors of matter and magnetic fields under some of the universe's most extreme conditions. For instance, stars are often thought of as uniformly hot bodies, but that's far from the full story. In reality, a star can be colder than the human body, which might surprise many. These cooler stars, known as brown dwarfs, are often referred to as failed stars because they lack the necessary mass to ignite hydrogen fusion, the process that fuels true stars like our sun. Without this fusion, brown dwarfs don't emit much visible light but still radiate heat. Their temperatures can range from a few thousand degrees Celsius, far below that of typical stars, to as cool as room temperature, and in some cases, even colder. Remarkably, some of the coolest brown dwarfs discovered so far dip below the average human body temperature of 37 degrees Celsius, 98 and 6 degrees Fahrenheit, further blurring the line between stars and planets. These extraordinary objects provide invaluable insights into star formation and the diversity of celestial bodies, challenging traditional definitions and expanding our understanding of the cosmos. Meanwhile, hypernovae are stellar explosions of an entirely different scale. These explosive events are vastly more energetic and luminous than typical supernova, releasing an immense amount of energy in a fraction of the time. A hypernova can output energy comparable to a regular supernova, but in a much shorter burst. These events are believed to result from the collapse of exceptionally massive stars, often leading to the formation of black holes. What makes hypernovae particularly fascinating is not just their overwhelming luminosity, but their connection to long-duration gamma-ray bursts, GRBs. GRBs are intense jets of gamma radiation blasted into space at nearly the speed of light, lasting anywhere from a few seconds to several minutes. These bursts are among the most powerful phenomena in the universe, detectable from vast cosmic distances. The mechanisms behind hypernovae and their association with GRBs are still an area of active research, but it is thought that the rapid rotation and powerful magnetic fields of these stars play crucial roles in focusing and propelling the energetic jets that characterize these events. By studying hypernovae and their aftermath, astronomers hope to unlock mysteries surrounding the life cycles of massive stars, the formation of black holes, and the nature of the universe's most violent explosions. In the same vein, pulsars are another class of celestial objects that offer a unique window into the extreme environments of the universe. A pulsar is essentially a highly magnetized rotating neutron star, emitting beams of electromagnetic radiation, which can include radio waves, X-rays, and even gamma rays from its magnetic poles. The misalignment of the pulsar's magnetic poles and rotation axis means that these beams sweep across the sky, and when one of these beams crosses Earth, we detect it as a regular pulse. This pulsating behavior is what gives pulsars their name. Pulsars rotate with such remarkable precision that some can rival atomic clocks in their accuracy. Their ability to serve as cosmic lighthouses, offering incredibly precise timing, makes them invaluable tools in astronomy. They allow scientists to study matter in the most extreme gravitational and magnetic fields, test theories of relativity, probe the interstellar medium, and even detect gravitational waves through highly accurate timing. The extreme precision of pulsar signals also holds promise for potential galactic-scale navigation systems. By tapping into the unique timing and electromagnetic signatures of each pulsar, astronomers envision a new way of navigating through the vastness of space, serving as beacons in the dynamic and ever-changing universe. Binary star systems, where two stars orbit a common center of mass, are also fundamental to our understanding of stellar behavior. These systems can range from close binaries, where the stars are so close that they exchange mass or even merge, to wide binaries, where the stars are far apart with minimal interaction. The significance of binary systems in astronomy is immense. These systems provide crucial insights into stellar dynamics, formation, and evolution. By studying binary stars, astronomers can precisely measure stellar masses and radii, which are essential for testing theories about stellar structure and evolution. The study of mass transfer in close binary systems has also revealed much about the life cycle of stars, especially the formation of exotic objects like neutron stars and black holes. Furthermore, binary star systems offer natural laboratories for testing fundamental physics, including the effects of gravity in extreme conditions. In fact, some binary systems, such as those containing pulsars or eclipsing binaries, offer unique opportunities to study the fundamental laws of physics at their most extreme. The life cycle of a star is a long, complex journey that can span millions to billions of years, depending on the star's mass. It all begins in a cold, dense molecular cloud, where gravity causes parts of the cloud to collapse and form a protostar. As the protostar accumulates mass, its temperature and pressure rise, eventually sparking nuclear fusion in its core. This marks the birth of a true star. During the main sequence phase, the star achieves a stable equilibrium, fusing hydrogen into helium. For stars like our Sun, this phase lasts around 10 billion years. As the star exhausts its hydrogen fuel, it transitions out of the main sequence. Stars like the Sun expand into red giants, fusing helium into heavier elements like carbon and oxygen. The most massive stars can fuse elements all the way up to iron. Eventually, the star sheds its outer layers, leaving behind a dense core. For stars up to about 8 times the mass of the Sun, this core becomes a white dwarf. For more massive stars, the collapse leads to a supernova explosion, leaving behind either a neutron star or, in the most extreme cases, a black hole. Throughout their lives, stars are not just nuclear fusion engines. They are dynamic, evolving objects that continually reshape the universe around them. The study of these celestial phenomena, from the cooler brown dwarfs to the explosive hypernovae, the precise pulsars, the intriguing binary systems, and the awe-inspiring life cycles of stars, is essential for deepening our understanding of the universe's most fundamental processes. Each discovery reveals more about the nature of matter, the forces shaping the cosmos, and the evolution of the stars that light up the night sky. But also, the cosmic forges are responsible for creating the heavier elements that form much of the universe, including the essential components necessary for life. The life cycle of a star plays a crucial role in the evolution of the cosmos, influencing the formation of new generations of stars and planetary systems. This process, which unfolds over millions to billions of years, has a lasting impact on the very fabric of the universe. One particularly intriguing concept in this cosmic narrative is the idea of dark stars. As of now, dark stars remain a theoretical concept. They haven't been directly observed, but the notion behind them is fascinating. Unlike conventional stars, which are powered by nuclear fusion, dark stars are believed to be fueled by the annihilation of dark matter within them. This form of energy production is radically different from the processes we are familiar with. The core of dark stars would consist of dark matter particles, which interact with gravity but not with electromagnetic radiation in the same way that normal matter does. This fundamental difference means that dark stars would not emit light in the usual wavelengths, making them extraordinarily difficult to detect with the technologies available to us today. However, scientists are not giving up on the search for these elusive objects. The possibility of dark stars' existence has led researchers to speculate about indirect methods for detecting them. For instance, the influence of dark stars on their surroundings could potentially reveal their presence. One of the most promising approaches involves looking at the cosmic microwave background radiation. Dark stars, if they exist, could alter the patterns in this radiation, leaving behind telltale imprints of their influence on the early universe. Furthermore, certain types of dark matter annihilation could produce unique gamma-ray signals. These signals could be detected by current or future gamma-ray observatories, offering a glimpse into the secret life of dark stars. The study of dark stars is still in its infancy, combining theoretical physics, advanced computer simulations, and indirect observational methods. Researchers aim to understand how these hypothetical stars would form, evolve, and impact their cosmic environments. If dark stars were discovered, it would open up unprecedented avenues of research into the nature of dark matter, the conditions of the early universe, and the diversity of stellar objects. Their discovery could dramatically reshape our understanding of the cosmos, revealing hidden layers of the universe that have long remained out of reach. Among the celestial cast, the most massive stars stand out as some of the most fascinating actors. These astronomical giants, often more than 100 times the mass of our Sun, are remarkable not just for their immense size, but also for their unique life cycles and the profound influence they exert on the universe. Born from the densest clouds of gas and dust, these stars live fast and die young by astronomical standards. Their lifespans, although spanning millions of years, are short compared to the billions of years that smaller stars like our Sun enjoy. Despite their brief existence, they shine with unparalleled intensity, radiating energy that can outshine entire galaxies. As these massive stars approach the end of their lives, they do so in a blaze of glory. Their deaths are among the most spectacular events in the universe, leading to phenomena such as supernovae, neutron stars, or even black holes. These final explosions release vast amounts of energy, dispersing heavier elements into the cosmos, which in turn seed the next generation of stars, planets, and life itself. The death of a massive star is not just an end, but a beginning, marking the continuous cycle of creation and destruction that drives the evolution of the universe. The birth and death of these colossal stars, as well as the theoretical dark stars, serve as reminders of the incredible forces at work within the cosmos. They are symbols of the universe's ever-changing nature, reminding us of the untold mysteries that still await our discovery. The more we learn about these cosmic wonders, the more we realize how little we truly know about the vast, infinite universe we inhabit. But their significance extends far beyond their dramatic finale. Throughout their existence, they are alchemists at the heart of cosmic evolution, forging every element heavier than hydrogen and helium. Through their explosive demise, they scatter these elements across the galaxy, seeding the very clouds that will give rise to new stars, planets, and potentially life itself. These massive stars, more than just awe-inspiring due to their size and power, play an essential role in the universe's narrative. They contribute to the complex process that makes the existence of everything from galaxies to living organisms possible. An exoplanet, a term denoting an extrasolar planet, refers to a planet that orbits a star beyond our solar system. These celestial bodies, nestled in the vast distance of space, have captured the imagination of scientists and astronomy enthusiasts alike. Their discovery represents one of the most thrilling advancements in modern astronomy, offering fresh insights into the possibility of life beyond our solar system. Unlike the planets within our own celestial neighborhood, exoplanets come in a staggering variety of sizes, compositions, and environments. Some of them sit comfortably in the habitable zones of their stars, where conditions may be just right for liquid water to exist, and with it, the potential for life. Thanks to the ingenuity and technological advancements, such as the Kepler telescope, thousands of these distant worlds have been identified since the first confirmed discovery in the 1990s. Each discovery adds a new piece to the vast cosmic puzzle, expanding our understanding of the universe's complexity and the widespread potential for planets like our own. The study of exoplanets not only challenges our notions of planetary formation and system architecture, but it also holds the promise of answering an age-old question: are we alone in the universe? Astronomers use a variety of ingenious methods to detect exoplanets, each one revealing different facets of these distant worlds. One of the most common techniques is the transit method. This approach observes the dimming of a star's light as an exoplanet passes in front of it. Even this minuscule dip in brightness allows astronomers to infer the planet's size and orbit. Another fascinating technique is the radial velocity method, often referred to as the wobble method. In this case, scientists detect the subtle movements of a star, either toward or away from us, caused by the gravitational pull of an orbiting planet. This method can provide valuable data about the planet's mass and the shape of its orbit. Direct imaging, a more challenging method, involves capturing visual images or spectra of exoplanets by blocking out the overwhelming light of their host stars. While currently only possible for a few exoplanets, this technique holds the promise of revealing a planet's atmosphere and chemical composition. Finally, gravitational microlensing relies on the gravitational field of a star and its orbiting planet, bending the light from a more distant background star. This temporary increase in brightness allows astronomers to detect the presence of an exoplanet. Each of these methods has its own strengths and weaknesses, but together they provide an evolving toolkit for astronomers to study distant planets and uncover the secrets of the cosmos. Through their efforts, the universe slowly reveals itself, one exoplanet at a time. But together, they form a truly powerful toolkit for astronomers, one that is reshaping our understanding of the cosmos and unlocking the mysteries of exoplanets scattered across the Milky Way. With recent discoveries, the title of the most Earth-like exoplanet is no longer fixed, constantly shifting as new worlds emerge from the depths of space, and our grasp on habitability deepens. Yet, one notable contender continues to spark curiosity: Kepler 4452b. Discovered by the Kepler Space Telescope, this exoplanet orbits a star remarkably similar to our Sun, residing in what is known as the habitable zone, that crucial Goldilocks region where conditions are just right for the potential presence of liquid water, a key ingredient for life as we know it. Kepler 452b is about 60% larger in diameter than Earth, earning it the designation of a super-Earth. Its orbital period of 385 days is tantalizingly close to Earth's, suggesting that the planet receives a similar intensity of sunlight. What makes Kepler 452b particularly intriguing is its positioning within the habitable zone of a G-type star, much like our own Sun. This star is thought to be about 1.5 billion years older than ours, raising questions about how life on such a world might have evolved, if at all. The potential for a life-sustaining atmosphere on Kepler 452b presents an exciting, albeit mysterious, possibility. While its surface conditions remain a mystery, the discovery of this exoplanet broadens our horizons, expanding our understanding of the diverse environments that might exist beyond our solar system. Kepler 452b tantalizes us with the possibility that Earth-like conditions may not be as rare as once thought, prompting astronomers to look deeper into the cosmos for signs of life on other worlds. Now let's dive into another mind-boggling discovery: circumbinary planets. These unique worlds orbit not just one star but two or more, making them a true cosmic oddity. The first confirmed circumbinary planet, Kepler 16b, was discovered in 2011, and it challenges everything we once knew about planetary formation. This extraordinary planet orbits two stars, located roughly 200 light-years from Earth, in a dynamic cosmic ballet. The two stars of the Kepler 16b system eclipse each other from our point of view, and the planet itself transits across both of their faces. Truly a remarkable spectacle. What makes circumbinary planets so fascinating is the way they challenge our traditional understanding of planetary formation. In a typical star system, planets form from the debris surrounding a single star, but these circumbinary planets exist in environments where two stars dominate the system. Their very existence forces scientists to reconsider how planets can arise in such complicated conditions, suggesting that planetary formation might be much more robust and adaptable than previously imagined. The discovery of these planets opens the door to a universe where planets can form in the most unexpected and complex environments, adding yet another layer of wonder to our understanding of planetary systems. Turning our gaze to the hot Jupiters, we encounter yet another category of exoplanets that has perplexed astronomers. Hot Jupiters are gas giants that rival or exceed the size of Jupiter, but orbit very close to their host stars. So close, in fact, that they complete an orbit in just a few Earth days. These planets are subject to intense heat, making their surfaces scorchingly hot, which is how they earned their name. The discovery of hot Jupiters was a surprise, presenting a significant paradox. According to traditional theories of planetary formation, gas giants like Jupiter are thought to form in the colder, outer reaches of a star system, where icy materials are plentiful. However, hot Jupiters defy this expectation, suggesting they either formed close to their stars or migrated inward from a much farther distance. The paradox of hot Jupiters has led to a surge in research aimed at understanding how these massive planets could move so close to their stars. This process, known as orbital migration, is one of the most exciting areas of study in exoplanetary science. It raises intriguing questions about the forces at play in young solar systems and the dynamics that could cause such massive planets to travel toward their parent stars. The discoveries surrounding hot Jupiters have reshaped our understanding of planetary formation and migration, revealing that nature can present scenarios far beyond our expectations and current knowledge. These planets continue to captivate astronomers, offering new insights into the nature of planetary systems and the incredible diversity of worlds that populate the cosmos. As we venture beyond our own solar system, it's worth considering the extreme and often bizarre weather patterns found on distant worlds. On Mars, massive dust storms can engulf the entire planet, obscuring the surface for months at a time. These storms are not just spectacular, but pose a challenge for future human exploration. Meanwhile, Venus offers one of the harshest environments in our solar system. With surface temperatures hot enough to melt lead and an atmosphere thick with carbon dioxide, Venus presents a hellish landscape. A runaway greenhouse effect traps heat, turning the planet into an oven, and sulfuric acid rains down from the sky, making it an almost impossible world to study, yet one that continues to intrigue scientists. Closer to home, Jupiter's weather is nothing short of dramatic. The Great Red Spot, a massive storm larger than Earth itself, has been raging for centuries with winds that can reach hundreds of miles per hour. This giant storm, a hallmark of the gas giant's turbulent atmosphere, is one of the most iconic features in our solar system. Jupiter's violent weather reminds us of the raw, the untamed power of nature in the cosmos, with its ever-changing storms providing both a challenge and a rich source of study for planetary scientists. The weather on other planets, both within and outside our solar system, reminds us of the vast diversity of environments in the universe. Whether it's the dust storms of Mars, the sulfuric acid rain of Venus, or the extreme conditions of faraway exoplanets, the universe never fails to amaze us with its infinite variety and unpredictability. As we continue to study these distant worlds, we gain a deeper appreciation for the fragile, yet resilient climate of our own planet and the importance of preserving it. But evaporates before ever reaching the ground due to the intense heat, creating an image of how extreme planetary weather can be in the cosmos. Looking even further afield to the exoplanets, the weather conditions can be far more exotic than anything we experience on Earth. Some worlds have rain made not of water, but of molten glass, which is blasted sideways by supersonic winds, while others may feature vast oceans of liquid methane or helium, a stark contrast to our own water-based seas. The diversity of weather across the universe highlights not only the vast range of physical conditions that exist on different planets, but also the incredible variability in atmospheric phenomena that can unfold depending on a planet's distance from its star, its chemical composition, and its internal and atmospheric dynamics. This exploration into extraterrestrial weather offers invaluable insight into planetary atmospheres, including our own. It reveals the unseen forces that play a pivotal role in shaping a planet's climate and weather patterns. In our quest to find planets that could harbor life, astronomers focus on identifying exoplanets located within their star's habitable zone, also known as the Goldilocks zone. This is the region around a star where the conditions might be just right, neither too hot nor too cold, for liquid water to exist on the planet's surface. Water, as we know, is one of the key ingredients for life. While several exoplanets have already been found in this desirable zone, confirming the presence of liquid water and the possibility of life-supporting conditions, requires far more detailed observations than our current technology typically allows. Nevertheless, a few notable candidates have sparked great interest. For instance, the TRAPPIST-1 system, located around 40 light-years away, contains several Earth-sized planets within its habitable zone, offering a tantalizing glimpse into the potential for liquid water, and by extension, life. Similarly, Proxima b, orbiting our closest stellar neighbor, Proxima Centauri, lies within the habitable zone and has become a prime candidate for further study regarding its ability to harbor life. While these discoveries are promising, determining whether these or any exoplanets truly possess conditions suitable for life remains a significant challenge. It requires advanced characterization, including the study of their atmospheres, surface temperatures, and the potential for biosignatures, elements or compounds that could indicate the presence of life. As such, while we've identified exoplanets that could potentially support life, confirming this possibility remains one of the foremost objectives in the field of astronomy. Upcoming missions and advancements in telescope technology are expected to provide the capabilities needed to tackle these questions head-on, bringing us closer to answering the profound question, are we truly alone in the universe? Rogue planets, also known as free-floating planets, are another mysterious class of celestial bodies that drift through space without orbiting any star. Unlike the planets in our solar system, which are anchored by the sun's gravity, rogue planets wander the galaxy unattached to any star or solar system. Their existence raises fascinating questions about the nature and formation of planetary bodies across the cosmos. Rogue planets are thought to form in one of two main ways. The first is similar to the formation of regular planets within a disk of gas and dust surrounding a young star. However, during the dynamic early stages of planetary system development, they can be ejected from their home systems due to gravitational encounters with other planets or by getting too close to their host star. Alternatively, rogue planets might form independently in a manner akin to stars from the collapse of a gas cloud. These rogue planets offer a glimpse into the incredible diversity of celestial bodies that exist in the universe, reminding us that the cosmos is far more complex and unpredictable than we could have ever imagined. But not acquiring enough mass to ignite nuclear fusion and become a star, rogue planets drift aimlessly through the vast emptiness of space. Despite their solitary existence, these wandering worlds are far from barren wastelands. In fact, some intriguing theories suggest that if a rogue planet possesses a thick atmosphere, it could trap enough residual heat to maintain relatively warm conditions. This could make these planets not just habitable, but potentially rich in life-sustaining environments. Moreover, if a rogue planet has moons or is geologically active, it might harbor subsurface oceans, kept warm by tidal forces or radioactive decay. These environments could provide the conditions necessary to support life beneath their icy crusts. The exploration of rogue planets thus represents an exciting new frontier in the search for extraterrestrial life, opening the door to a vast, largely unexplored domain of the galaxy. However, detecting and studying these elusive objects presents significant challenges. Without a luminous star to illuminate them, rogue planets remain hidden from conventional observation methods. To infer their presence, scientists must rely on sophisticated techniques such as gravitational microlensing, where the gravity of a rogue planet distorts the light of distant stars, revealing its location. Meanwhile, the moons orbiting the planets in our own solar system boast a fascinating variety of features that underline the diversity of celestial bodies. Take Jupiter's moon Europa, for example, which is enveloped in a thick shell of ice. Beneath this icy crust lies a vast saltwater ocean, believed to contain twice as much water as Earth's oceans. This subsurface ocean makes Europa one of the most promising candidates in the search for extraterrestrial life. Another of Jupiter's moons, Io, holds the title of the most volcanically active body in the entire solar system. Its sulfurous eruptions are so powerful that they can be seen with telescopes from Earth, offering a glimpse into the extreme processes taking place on its surface. Over in Saturn's orbit, Titan stands out as the only known moon with a dense atmosphere, mostly composed of nitrogen. Its surface is dotted with lakes and rivers made of liquid methane and ethane, giving it the eerie reputation of an Earth-like world, albeit with a frigid alien chemistry. Nearby, Enceladus, another of Saturn's moons, ejects massive plumes of water ice from its south pole into space, providing further evidence of a subsurface ocean that might also harbor the conditions necessary for life. Not to be left out, Neptune's moon, Triton, orbits in a retrograde direction, suggesting it was once a dwarf planet that was gravitationally captured by Neptune after wandering through the Kuiper Belt. Triton's geysers are believed to eject nitrogen gas and dust from beneath its surface, hinting at internal processes that remain a mystery. These moons are not only remarkable for their diverse environments, but also offer invaluable insights into the geological and atmospheric phenomena that occur beyond Earth. They continue to challenge and expand our understanding of planetary science, pushing the boundaries of what we know about the cosmos. The search for exomoons, moons that orbit planets outside our solar system, adds yet another layer of intrigue to our understanding of the universe. While detecting exomoons is notoriously difficult due to their small size and the glare of their host stars, theoretical models and observations suggest that exomoons could be even more common than exoplanets. Their discovery could offer new clues about the formation and evolution of planetary systems and help us understand the potential for habitable environments far beyond our own planet. Detecting exomoons involves techniques similar to those used for exoplanets. One of the most promising methods is the transit method, which observes the dimming of a star's light as a planet, and possibly its moon, passes in front of it. This dimming could be indicative of the moon's presence either through additional dips in brightness or changes in the timing and duration of the transit. Another technique, gravitational microlensing, exploits the gravitational pull of a planet-moon system passing in front of a distant star, magnifying and distorting the star's light in a way that can reveal both the planet and its moon. Despite the challenges of observing these distant moons, the first potential exomoon detections have already been reported, sparking a flurry of interest in confirming their existence and studying their properties. If confirmed, the discovery of an exomoon would be a monumental milestone in the field of astronomy, opening up new possibilities for understanding the diversity of celestial bodies and the potential for life in environments that might resemble those of our own solar system. After all, moons in our solar system have already proven to be some of the most promising habitats beyond Earth. String theory, a theoretical framework that aims to unify quantum mechanics and general relativity, introduces an entirely new way of thinking about the fundamental forces of nature. In this theory, the point-like particles of traditional particle physics are replaced by one-dimensional objects known as strings. These strings can vibrate at different frequencies, much like the strings of a musical instrument, and these vibrations are thought to correspond to the various particles and forces of the universe. In essence, string theory provides a potential unification of the two pillars of physics: quantum mechanics, which describes the very small, and general relativity, which explains the very large. This pursuit of a single unified theory continues to drive research in theoretical physics and remains one of the most fascinating endeavors in the scientific community, but which currently do not align under a single theory. String theory is compelling because it could provide a so-called theory of everything, offering an overarching explanation of the fundamental forces and components of the universe. String theory suggests the existence of additional spatial dimensions beyond the three we experience daily, as well as parallel universes within a multiverse. It also offers potential insights into the very early universe, moments after the Big Bang, a period that remains mysterious and largely inaccessible to traditional theories of physics. Despite its elegance and the promise it holds, string theory faces criticism due to the current lack of experimental evidence and the challenge of testing its predictions. The energies required to probe the scales where string effects would become noticeable are far beyond what current particle accelerators can achieve. Nonetheless, string theory continues to be a rich field of research, stimulating advancements in mathematics and theoretical physics. It remains a leading candidate for unifying the fundamental forces of nature into a single framework, potentially revolutionizing our understanding of the universe. Wormholes are theoretical passages through space-time that could create shortcuts for long journeys across the universe. In essence, they are predicted by the equations of general relativity, which describes the gravitational interaction in the universe and allows for the possibility of bending and folding space-time. A wormhole would have at least two ends connected by a tunnel-like geometry, offering a direct path between vastly distant regions of space or even different times. The allure of wormholes lies not just in their science fiction appeal, but also in their potential to challenge our understanding of physics, allowing for instantaneous travel across the cosmos, or providing a bridge to other universes. However, despite their theoretical underpinnings, the existence of wormholes remains speculative, and no empirical evidence has been found to date. Major hurdles include the stability of these structures. According to current theories, maintaining a traversable wormhole would require exotic matter with negative energy density, something not known to exist in the quantities needed. Furthermore, creating or discovering a wormhole large enough for spacecraft to travel through and ensuring it is stable enough for safe passage presents another significant challenge. Thus, while wormholes tantalize with the possibilities of warp speed travel and interstellar exploration, their existence and practicality lie squarely in the realm of speculation and theory at this point in time. The study of wormholes continues to inspire researchers, pushing the boundaries of theoretical physics and our understanding of the universe. The concept of time travel has long fascinated both scientists and the public, often explored in the context of cosmic phenomena. Within the framework of physics, according to the theories of relativity proposed by Albert Einstein, time is not a constant, but varies according to the speed at which an observer is moving and the strength of gravitational fields they experience. This relativistic view of time suggests that under extreme conditions, such as those near black holes or when traveling at speeds close to that of light, time can dilate or slow down relative to an observer in a different setting. A phenomenon confirmed by experiments, these well-established principles lay the foundation for some of the more speculative ideas that have been explored. For instance, using wormholes, hypothetical passages through space-time, to travel between different points in space and time. Another theoretical possibility involves cosmic strings, hypothetical defects in the fabric of space-time left over from the early universe. If these cosmic strings exist, and two of them were to pass close to each other, they could, in theory, create conditions that warp space-time in such a way as to allow for time loops or travel. However, the feasibility of using such cosmic phenomena for time travel ventures deep into the realm of speculation. Current scientific understanding holds that even if these phenomena do permit time travel in theory, the technological and energy requirements to harness them are far beyond our present capabilities. Additionally, various paradoxes associated with time travel, such as the grandfather paradox, raise questions about the logical consistency of these scenarios. Quantum entanglement is a phenomenon in the realm of quantum physics where pairs or groups of particles become interconnected such that the state of one, whether it be their position, momentum, spin, or polarization, cannot be described independently of the state of the others, even when the particles are separated by large distances. This means that a change to one particle instantaneously affects its entangled partner, a phenomenon Albert Einstein famously referred to as spooky action at a distance. This counterintuitive aspect of quantum mechanics challenges our classical understanding of how the universe works, suggesting that particles can be deeply connected through the fabric of space-time in ways that transcend the conventional limits of space and speed. Quantum entanglement occurs naturally and plays a fundamental role in various processes in space. For example, during the early stages of the universe following the Big Bang, when particles were being formed and everything was much closer together, the conditions were ripe for entanglement. The cosmic microwave background radiation, a relic from the Big Bang, carries imprints of these early quantum interactions. Additionally, entanglement plays a crucial part in the fusion processes inside stars, including our Sun, where the extreme conditions facilitate quantum behaviors. Moreover, quantum entanglement has profound implications for the field of quantum computation and communication, suggesting methods for secure communication channels over vast distances, potentially outpacing the speed and security of traditional electronic systems. While harnessing quantum entanglement for practical applications remains an area of ongoing research and development, its natural occurrence in space continues to inspire and challenge our understanding of the universe, driving forward both theoretical exploration and technological innovation. The theory of cosmic inflation serves as a compelling explanation for the state of the early universe. Picture this: Less than a blink after the Big Bang, the infant universe underwent a brief yet explosive expansion that stretched space-time to unimaginable scales, laying the groundwork for the universe as we know it today. But it was stupendous, a true ballooning in size by a factor that stretches the imagination, a transformation on a scale so mind-boggling that it's difficult for us to fully grasp. This phase, known as cosmic inflation, might have lasted no longer than a fraction of a second, a mere 10 coup to 32 seconds. In that infinitesimal slice of time, the universe expanded faster than the speed of light itself, smoothing out all irregularities, ironing away any imperfections, and setting the stage for the vast, homogeneous expanse we observe today. Cosmic inflation offers a profound explanation for why the universe in its early stages was so remarkably uniform. It accounts for the even temperature of the cosmic microwave background radiation and the distribution of galaxies scattered across the sky. This rapid expansion stretched and flattened the curvature of space-time, laying the groundwork for the universe's later, more gradual expansion. Though cosmic inflation remains a theory, its predictions have been remarkably accurate. It has passed numerous observational tests, providing a glimpse into the universe's first fleeting moments, those moments that define the very structure of everything we know. Yet, one of the most mind-bending mysteries that persists in the cosmos revolves around antimatter, that elusive counterpart to matter. In the early moments of the universe, matter and antimatter were created in equal amounts. Yet today, we find ourselves in a universe dominated overwhelmingly by matter. This imbalance is one of the greatest puzzles in physics. Antimatter behaves like a mirror image of regular matter, identical in mass but opposite in charge. When they come into contact, they annihilate one another, releasing immense energy in the process. This characteristic is not just a curious fact. It plays a vital role in the high-energy processes that occur in the universe. For example, the annihilation of positrons, antimatter's counterparts to electrons, produces gamma rays, which are the most energetic form of light. This phenomenon gives astronomers a powerful tool for studying the universe's energetic events, like the rapid pulsations of black holes that generate these particles. Yet, the true enigma lies in the imbalance between matter and antimatter. What could have happened in the early universe to favor the slight excess of matter that led to the universe as we know it today? As scientists continue to unravel this mystery, antimatter remains one of the keys to understanding the fundamental symmetries of the universe, and perhaps the conditions that gave birth to the cosmos. The concept of alternate dimensions has long intrigued both scientists and dreamers alike. Could there be realities beyond the familiar three-dimensional world we experience? Theoretical physics, especially through the lens of string theory, suggests that our universe could be just one of many, embedded within a larger, multidimensional fabric. String theory proposes that the particles which make up everything in our universe are not point-like dots, but tiny, vibrating strings. These strings vibrate at different frequencies, akin to the notes on a musical instrument, with each vibration corresponding to a different particle. What's truly groundbreaking about string theory is its requirement for extra dimensions, 10 or 11 in total. These extra dimensions are essential for the mathematics to work out. But here's the kicker. These dimensions are not something we experience directly. They are believed to be compactified or folded at incredibly small scales. Imagine a garden hose from a distance, looking like a one-dimensional line, but up close you realize it's three-dimensional, with a tiny circular dimension wrapped around every point. In a similar fashion, these extra dimensions might be curled up at every point in space, so small that we can't detect them with current technology. The idea of alternate dimensions opens up profound possibilities for answering some of physics' most perplexing questions. Could they help explain the unification of gravity with the other fundamental forces, or perhaps shed light on the nature of dark matter and dark energy? While the existence of these extra dimensions remains speculative, the pursuit of their understanding drives much of today's cutting-edge research in theoretical physics. This search represents a quest to uncover the deepest truths of our universe. Gravitational waves, ripples in the very fabric of space-time, are another awe-inspiring aspect of the cosmos. Predicted by Einstein in 1916 as part of his general theory of relativity, gravitational waves are caused by some of the most violent and energetic processes in the universe. When massive objects like black holes or neutron stars collide, they send out waves through space-time, much like a stone dropped in a pond sends ripples across the water's surface. However, these waves are faint, incredibly faint, and until recently they were beyond our technological reach. That is, until September 14th, 2015. On that date, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting the first direct signal of gravitational waves. This signal came from two black holes, each about 30 times the mass of the Sun, spiraling toward one another, merging and sending a ripple through the fabric of space-time from 1.3 billion light-years away. This monumental breakthrough confirmed Einstein's long-standing prediction and opened an entirely new window onto the cosmos. Gravitational wave astronomy is revolutionizing our understanding of the universe. It allows us to observe cataclysmic events, such as the merging of black holes that were previously invisible to our telescopes. Through these waves, scientists can now study gravity, the behavior of black holes, and even peer into the origins of the universe itself. This discovery heralds a new era of astronomy, one where we can listen to the cosmos and explore the universe in a way we once thought impossible. As we look to the skies, we are bombarded by cosmic rays, high-energy particles traveling through space at nearly the speed of light. These particles primarily consist of protons and a small fraction of heavier atomic nuclei, as well as some antimatter particles. They originate from a variety of sources: the Sun, distant supernova, and possibly even more exotic sources like supermassive black holes at the centers of galaxies. These cosmic rays carry invaluable information about high-energy physics, offering a glimpse into conditions that are impossible to replicate in our laboratories. Some cosmic rays are so energetic that they possess energies millions of times greater than those achievable in the world's most powerful particle accelerators, such as the Large Hadron Collider. By studying cosmic rays, we gain access to a natural laboratory that allows us to probe the fundamental forces and particles that govern the universe. When cosmic rays collide with the Earth's atmosphere, they produce secondary particles, including neutrinos and muons, which can be detected by scientists. By observing these particle showers, physicists can test predictions in particle physics, offering clues about the fundamental laws of the universe. Despite the Big Bang Theory being the most widely accepted explanation for the origins of the universe, several mysteries remain unsolved. One of the most profound questions revolves around the actual cause of the Big Bang itself. What triggered the monumental explosion that set the universe in motion? Current theories explore various possibilities, from the landscapes of string theory to the concept of quantum fluctuations, suggesting that there may be more to the birth of the universe than we yet understand. The search for answers continues to push the boundaries of scientific inquiry, keeping the cosmos as enigmatic and awe-inspiring as ever. But a definitive answer remains elusive. Another significant mystery in the universe is the matter-antimatter asymmetry. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other upon contact, leaving the universe devoid of any substantial matter. Yet, here we are. Our very existence and the observable universe are a testament to an imbalance between matter and antimatter. The question is, why does this imbalance exist? And how did it come to be? Scientists continue to probe deeper into this enigma, but the full explanation remains out of reach. The horizon problem adds another layer to this cosmic puzzle. It raises the question, how is it that regions of the universe, which are so far apart that they should have never been in contact with each other, appear to be at the same temperature? This uniformity is perplexing, as it suggests some form of faster-than-light communication or interaction in the early universe, something that defies our current understanding of physics. This puzzle led to the development of the inflationary theory, proposing a period of rapid expansion in the moments following the Big Bang. While inflation offers a potential solution, it too raises its own questions. What triggered this sudden expansion, and what stopped it? Finally, the nature of dark matter and dark energy two invisible forces that make up about 95% of the universe's total mass and energy content, continues to baffle scientists. These enigmatic components neither absorb, reflect, nor emit light, making them incredibly difficult to detect. Despite their elusive nature, their gravitational effects are undeniable. Dark matter influences the rotation of galaxies and the distribution of galaxies in clusters, while dark energy is responsible for the accelerated expansion of the universe. Understanding these forces is crucial to unlocking the deeper mysteries of the cosmos. As technology advances and new theories emerge, scientists are hopeful that we may one day uncover the true nature of these invisible forces. Fast radio bursts, FRBs, represent one of the most captivating and mysterious phenomena in the universe. Discovered in 2007, these intense bursts of radio waves last only milliseconds, yet in that brief flash, they release as much energy as the sun does in nearly an entire day. What's even more intriguing is that these bursts come from sources located billions of light years away, beyond the Milky Way. Their origins remain largely unknown, which has fueled a wide array of theories and ongoing research. What makes FRBs particularly puzzling is their fleeting nature and the vast distances they travel to reach Earth, suggesting an origin of extraordinary energy. Theories about their sources range from highly magnetized neutron stars and black hole mergers to more speculative ideas, such as highly advanced extraterrestrial civilizations. Some FRBs are one-time events flashing once and never to be seen again, while others repeat in bursts, deepening the mystery. The study of FRBs is an exciting and rapidly developing field. Repeaters, unlike one-off events, offer more opportunities for observation, like allowing astronomers to gather more data about their properties and potential origins. In fact, efforts to trace the bursts back to their host galaxies have begun to yield results. Some bursts have been linked to very specific types of galaxies and particular cosmic conditions, providing tantalizing hints that could eventually reveal the true cause of these signals. As technology and detection methods continue to improve, the hope is that the riddle of FRBs will eventually unravel, offering not just an explanation for these elusive bursts, but a deeper understanding of the forces and events that shape our universe, but also providing new insights into the physics of the universe. The discovery and study of fast radio bursts, FRBs, underscore the vastness of our cosmos and humanity's relentless pursuit of understanding its mysteries. One of the most intriguing phenomena in this journey is the WOW signal, detected on August 15, 1977, by the Big Ear Radio Telescope at Ohio State University. This mysterious signal, which lasted 72 seconds, remains one of the most captivating episodes in the ongoing search for extraterrestrial intelligence. Its appearance as a strong, narrowband radio signal aligned perfectly with the expected characteristics of an interstellar broadcast. Astronomer Jerry R. Eman, who first recorded the signal, was so astounded that he scrawled the word "wow" in the margins of the printout, cementing the signal's place in history. However, despite its tantalizing implications, the WOW signal has never been detected again. This has led to widespread speculation and investigation into its origin, with numerous theories about what might have caused it. One of the most compelling explanations is that the signal could have emanated from a natural celestial source, rather than an artificial one from an extraterrestrial civilization. Some suggest that a passing comet might have been responsible, as comets can emit radio waves when their hydrogen clouds are ionized by the sun. This theory gained traction when it was discovered that two comets, 266P Christensen and P208Y2, were in the vicinity of the signal's origin point in 1977. However, attempts to detect similar signals when these comets returned were unsuccessful, casting doubt on this possibility. Another plausible natural explanation is that the WOW signal might have come from a magnetar, a type of highly magnetic neutron star known for emitting intense bursts of radio waves. Yet the brief nature of the signal and the failure to detect it again make this hypothesis equally difficult to confirm. While the notion of an alien broadcast remains enticing, the lack of a repeated signal and the inability to conclusively identify its source have led most scientists to lean toward natural astronomical phenomena. Despite decades of searching, the true origin of the WOW signal remains an unsolved mystery, encapsulating the thrilling and elusive nature of space exploration. It stands as a reminder of the vast, uncharted frontiers of our universe and the ever-present quest to uncover the unknown. Space exploration has been a triumph of human ingenuity, yet it has not come without its share of strange anomalies and unsolved mysteries. Among the most perplexing is the Pioneer anomaly, which involves the Pioneer 10 and Pioneer 11 spacecraft. These spacecraft, launched in the early 1970s to study the asteroid belt and Jupiter, began to deviate from their expected paths once they passed Mars. After years of detailed analysis, scientists found that both spacecraft were experiencing a small, unexplained deceleration. The anomaly baffled scientists and, for a time, various theories, including the possibility of unknown physical phenomena, were proposed. However, after extensive study, a consensus emerged. The anomaly was most likely caused by anisotropic thermal radiation pressure. In essence, heat emitted by the spacecraft themselves was gently pushing them off course. This discovery highlights the complexity of space travel and the subtle influences of physics in the vacuum of space. Another mysterious incident occurred with the Mars Global Surveyor, MGS, a spacecraft that had been mapping the Martian surface for nearly a decade. In 2006, the MGS unexpectedly lost communication with Earth. Initial investigations pointed to a software update months before the loss of contact, which might have caused the spacecraft's solar panels to misalign, disrupting its power system and cutting off communication. While this explanation fits many of the observed anomalies, it doesn't account for all aspects of the event, leaving a lingering sense of mystery about what truly happened. The loss of MGS serves as another reminder that even in the most meticulously planned space missions, the unknown can strike, keeping scientists and explorers on edge. The mysteries of space, from the enigmatic WOW signal to the unexplained anomalies of interplanetary missions, continue to fascinate and challenge us. Each new discovery pushes the boundaries of our understanding, inviting us to question the very nature of the cosmos and our place within it. The quest for answers is far from over, and as our technology advances, so too does our ability to peel back the layers of the universe's most elusive secrets. For now, we remain in awe, always on the lookout for the next cosmic clue that might unlock the answers to the questions that have haunted humanity for centuries. And so, as we venture deeper into the unknown reaches of space, these anomalies serve as stark reminders of the vast challenges we face. They underscore the unpredictable nature of the cosmos and highlight the limits of our understanding, despite decades of progress. Each unexplained event pushes the boundaries of our curiosity, urging us to dig deeper and question even more. Even with the most advanced planning and technology, the universe retains its power to surprise, throwing unexpected complexities into our path. These phenomena challenge us, yet fuel the dreams of space exploration. The dream of venturing beyond our solar system has captivated humanity for centuries, igniting a sense of wonder and sparking imaginations. It pushes the very limits of both scientific ambition and human perseverance. While the concept of interstellar travel is still grounded firmly in the realm of science fiction, there are growing efforts and proposed missions that may one day bring us closer to that seemingly unreachable goal. One of the most daring of these proposals is Breakthrough Starshot, an initiative that aims to send tiny, light-propelled spacecraft to Alpha Centauri, the closest star system to Earth. Located more than 4 light-years away, Alpha Centauri has long been a point of fascination for scientists and dreamers alike. Breakthrough Starshot seeks to develop fleets of nanocrafts, tiny, high-tech probes with light sails designed to be propelled by powerful ground-based lasers. These craft would travel at a significant fraction of the speed of light, making the journey to Alpha Centauri in just a few decades, potentially providing humanity with its first close-up images of another star system. This ambitious plan could unlock unprecedented data about the stars and possibly even the planets that orbit them. While Breakthrough Starshot focuses on interstellar distances, NASA's Interstellar Probe, though not aiming for another star, would explore the outermost reaches of our solar system and beyond. This mission, building on the legacy of the Voyager probes, would push out into the vast emptiness of interstellar space to study the heliosphere boundary, the bubble-like region of space dominated by our sun's solar wind. By gathering data on this region, the probe could provide invaluable insights into the environment of our galaxy and help us better understand the conditions that exist in the space between stars. Similarly, the Nanograph project, while not a traditional space mission, aims to deepen our understanding of the universe's grand structure by investigating the gravitational waves produced by supermassive black hole collisions in distant galaxies. This research could reveal crucial details about how galaxies evolve and help lay the groundwork for future interstellar exploration by mapping the cosmic ocean we may one day seek to navigate. But these missions, bold as they are only the beginning. The technical challenges they present are monumental, and achieving their goals could take decades, even centuries. Yet, they represent humanity's first tentative steps toward exploring the vastness of interstellar space. Each project pushes the limits of current technology and physics, gradually expanding our understanding of what is possible and bringing the unreachable stars just a little bit closer. As we continue to explore the deepest mysteries of the cosmos, we must also turn our attention to the invisible forces that govern the universe: dark energy and dark matter. Together, these two enigmatic components make up about 95% of the universe's mass energy content. Understanding them requires some of the most cutting-edge technology and innovative techniques we can devise. Since dark matter does not interact with electromagnetic radiation in a way that can be directly observed, researchers must rely on indirect methods. Scientists use deep underground laboratories to attempt to detect dark matter particles by shielding their detectors from cosmic rays and other background noise. In addition, observations of galaxies and the bending of light around massive objects, known as gravitational lensing, offer clues about the distribution and properties of dark matter. Dark energy, the mysterious force thought to be driving the accelerated expansion of the universe, is studied by examining distant supernovae, galaxy clusters, and the cosmic microwave background radiation. These observations help scientists understand how the expansion of the universe has changed over time and offer critical insights into the forces at play in the universe's ever-expanding fabric. Despite the immense unknowns and technical hurdles, these projects mark humanity's most ambitious efforts to explore not just the stars, but the very foundations of the universe itself. Each discovery, each step forward, brings us closer to unraveling the vast, intricate mysteries of the cosmos. In the near future, missions like the UCLI satellite and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will map the universe with a level of detail that's never been achieved before. These groundbreaking initiatives aim to shed light on the enigmatic forces of dark energy, fundamentally shaping our understanding of the cosmos and its large-scale structure. The discoveries and insights gleaned from these missions may push us to reconsider and refine the very foundations of physics, potentially challenging the established standard model of particle physics and general relativity. By pushing the boundaries of both technology and theory, scientists are determined to unlock the greatest mysteries of the universe: dark matter, dark energy, and the nature of space itself. The future of astronomy is incredibly promising, with cutting-edge telescopes and observatories set to revolutionize how we perceive the universe. The James Webb Space Telescope, launched in December 2021, is already on the cutting edge of these advancements. As the successor to the Hubble Space Telescope, it is designed to observe the universe in infrared wavelengths, enabling scientists to peer through dust clouds and witness the birth of stars and planetary systems. Its ability to explore the atmospheres of distant exoplanets raises the possibility of discovering signs of extraterrestrial life. Moreover, it offers a unique vantage point to look back in time, observing the earliest galaxies that formed after the Big Bang. But Webb is not alone in the race to unveil the mysteries of the universe. The extremely large telescope, ELT, under construction in Chile, is set to become the world's largest optical and near-infrared telescope. When it comes online later this decade, its 39-meter primary mirror will gather 13 times more light than current telescopes, offering unprecedented detail on planets orbiting distant stars, and even allowing for the direct imaging of exoplanets. The Square Kilometer Array, SKA, an ambitious radio telescope project, will also contribute to the exploration of the cosmos. With thousands of dishes and millions of low-frequency antennas spread over vast distances, it will study cosmic phenomena such as pulsars, the magnetic fields of galaxies, and the nature of fast radio bursts. Additionally, SKA will provide valuable insights into the early universe, including clues about the era of reionization and the cosmic web. Meanwhile, the Vera C. Rubin Observatory, still under construction, will conduct the LSST, capturing detailed images of the entire sky every few nights for a decade. This will result in an unparalleled astronomical data set, revealing thousands of new objects, from potentially hazardous asteroids to transient phenomena like supernova, while also probing the mysteries of dark matter and dark energy. These missions represent the next frontier in observational astronomy, each offering a unique perspective on the universe's deepest secrets. However, venturing beyond observational astronomy, the dream of interstellar travel, once thought to be the stuff of science fiction, is gradually becoming a feasible goal. The concept of interstellar travel hinges on the development of propulsion systems that can achieve the enormous velocities required to traverse the vast distances between stars in a reasonable time frame. To accomplish this, new propulsion technologies must be developed to overcome the colossal challenges posed by such ambitious missions. One promising avenue is nuclear propulsion, which holds the potential to be far more efficient than current chemical rockets. Nuclear fission propulsion could significantly reduce the travel time to nearby star systems. Even more ambitious is nuclear fusion, the same process that powers our sun, which could offer an incredibly powerful propulsion system, possibly allowing spacecraft to reach a significant fraction of the speed of light. Breakthrough Starshot, another initiative, proposes using powerful ground-based lasers to accelerate small, lightweight probes to relativistic speeds, sending unmanned spacecraft to nearby stars within a few decades. While antimatter propulsion remains far beyond our capabilities, the theory behind it is enticing. Antimatter annihilation produces enormous amounts of energy, which could potentially propel spacecraft at near-light speeds. But producing, storing, and utilizing antimatter in the quantities needed for interstellar travel is a monumental challenge that will require significant technological breakthroughs. In addition to propulsion, interstellar travel presents challenges that extend far beyond the realm of propulsion systems. Life support systems, energy supply, and shielding from cosmic rays and interstellar dust are critical components that need to be addressed. Self-sustaining life support systems and compact, highly efficient energy storage and generation technologies will be required to support long-duration missions. Moreover, robust shielding will be necessary to protect astronauts or sensitive equipment from the hazards of deep space. Robotics and artificial intelligence, AI, will also play an indispensable role in the future of interstellar travel. AI and automation can assist in constructing spacecraft, handling complex operations during the journey, and reducing the cost and complexity of space launches. Additionally, robotics can help perform tasks beyond human reach, ensuring the success of missions that last decades or even centuries. While interstellar travel remains a distant dream, rapid advancements in fields like propulsion technology, material science, robotics, and AI are gradually bringing it closer to reality. However, sending spacecraft to other galaxies presents challenges that amplify these difficulties on an unprecedented scale. The vast distances between galaxies are the most significant obstacle, with even our closest neighboring galaxy, Andromeda, sitting roughly 2.5 million light-years away. Achieving such an endeavor would require propulsion systems far more advanced than anything we currently have, systems capable of maintaining incredibly high speeds over millennia, if not millions of years. One of the most daunting aspects of intergalactic travel is the immense energy required to propel a spacecraft across such vast distances. Current methods, including chemical rockets and even speculative future technologies like nuclear or antimatter propulsion, fall dramatically short of the energy required. Developing propulsion systems that can accelerate a spacecraft to a significant fraction of the speed of light and then decelerate it as it approaches its destination is a monumental engineering challenge that demands breakthroughs in physics and technology. Beyond propulsion, the spacecraft would need to be equipped with a navigation system capable of operating across the immense distances between galaxies, as well as a communication system that can send data back to Earth across millions of light years. The spacecraft's design would also have to withstand the ravages of time during a journey lasting thousands or even millions of years. Components would need to be incredibly reliable, potentially even capable of self-repair or regeneration, a technology far beyond our current capabilities. Finally, the rationale for embarking on such a mission would need to be compelling enough to justify the immense investment of resources and time. Robotic probes may one day make it possible to expand our understanding of the universe by exploring galaxies that are currently unreachable. However, human intergalactic travel at this stage remains speculative, resting in the realm of science fiction. Still, as we make progress in technology and innovation, we may one day find ourselves taking the first steps on this extraordinary adventure, charting a path to the stars that will push the limits of human ingenuity. But also, it's a profound expansion of our understanding of physics and the universe. While the prospect of intergalactic travel is undoubtedly an exciting one, it remains, for the foreseeable future, a distant dream. Yet, this dream beckons us to push the boundaries of our imagination and scientific ambition, urging humanity to reach for the stars, quite literally. And as we look to the cosmos, we can't help but wonder, what is out there, waiting to be discovered? I apologize for not being able to provide real-time updates or the most current information, including the latest groundbreaking discoveries from the James Webb Space Telescope, JWST. However, as of my last update, the JWST, launched on December 25th, 2021, was designed to make unprecedented observations of the universe. Its mission objectives span from unraveling the formation and evolution of galaxies and stars to probing the atmospheres of exoplanets that could potentially harbor life. With its advanced technology, the JWST is poised to make significant discoveries and offer deep insights into the cosmos's earliest epochs, including observing the formation of the first galaxies and stars. But the JWST doesn't just study the past. It will also peer into the future, studying the life cycle of stars and the creation of elements essential for life. Thanks to its sophisticated suite of instruments and ability to observe in the infrared spectrum, the JWST will provide a view of the universe far beyond what we've seen before. This telescope holds the promise of answering some of the most profound questions of our existence, including whether life could be thriving on distant planets. As it embarks on its mission, it is expected to make discoveries that will reshape our understanding of the universe. To stay up to date with the latest findings from the JWST, I recommend regularly checking updates from NASA and other astronomical research institutions involved in the project. In the vast expanse of the cosmos, artificial intelligence, AI, has become an indispensable ally in the quest to unravel the mysteries of the universe. One of the most significant breakthroughs facilitated by AI is the detection of exoplanets, planets that orbit stars outside our solar system. Traditionally, astronomers had to painstakingly sift through massive data sets to identify the faint signals that might indicate the presence of these distant worlds. However, with the advent of machine learning algorithms, this process has been revolutionized. AI systems are now capable of recognizing patterns in the data that even the most experienced human eyes might miss. For example, using data from NASA's Kepler Space Telescope, an AI model identified 2 new exoplanets that had been overlooked in previous analyses. This is just one instance of how AI is exponentially expanding our knowledge, allowing us to discover more than 4,000 exoplanets to date. But AI's role doesn't stop there. Beyond exoplanet discovery, AI is also being used to process the enormous volumes of data generated by telescopes worldwide. From tracking asteroids to uncovering the very structure of the universe, AI is increasingly integral to astronomical research. As our computational methods grow more sophisticated, the role of AI in space exploration will undoubtedly increase, potentially leading to breakthroughs that we can scarcely imagine today. This powerful synergy between technology and human curiosity is paving the way for the next era of cosmic discovery, offering us glimpses into the unknown reaches of space that were previously beyond our grasp. The discovery of a planet entirely covered in water would be nothing short of astonishing, offering a glimpse into the immense diversity of planetary systems and challenging our understanding of habitability and the potential for life beyond Earth. Such a world, often referred to as an ocean planet or water world, would represent a dramatic departure from the rocky terrestrial planets like Earth that we're more familiar with. The scientific implications of discovering a water-covered planet would be profound. Researchers would be eager to study its atmosphere, its climate, and of course, the depths of its vast ocean. Questions about the composition of the water, the stability of its climate, and whether its conditions could support life would spark a flurry of investigation. Water is a critical ingredient for life as we know it, and the discovery of such a planet would make it a prime candidate in the search for extraterrestrial life. Scientists would race to understand the possibility of diverse ecosystems thriving beneath its surface, with life potentially evolving in ways we've never before considered. Such a discovery could change our view of the universe, highlighting the incredible diversity of environments where life might exist. This journey into the unknown is not just about finding other Earth-like planets or exoplanets that could harbor life. It's about pushing the limits of human knowledge, exploring the boundaries of what's possible, and expanding our understanding of the cosmos. Whether it's through the groundbreaking discoveries made by the JWST, the revolutionary power of AI, or the tantalizing possibility of discovering water worlds, humanity is on the cusp of a new era in space exploration. Every step forward brings us closer to the answers to some of our most profound questions. Are we alone in the universe? What other worlds await our discovery? And how will these revelations shape our future as a species? The answers, it seems, are just beyond the horizon, waiting for us to find them. Scientists are increasingly drawn to the possibilities of life beyond Earth, particularly on planets or moons that may seem inhospitable at first glance. When considering the potential for life, researchers look beyond microbial organisms, envisioning the existence of complex life forms that could adapt to the unique conditions of distant oceanic worlds. Such planets would challenge our traditional understanding of what constitutes a habitable environment. While most of the search for life in the cosmos has centered around Earth-like planets with surface water, a world completely covered by oceans presents an entirely different scenario, one that could drastically alter how we view life beyond our planet. This shift in perspective opens up exciting new avenues for exploration. A water-covered planet would suggest that life might thrive in environments far removed from anything we've ever encountered. No longer would the search for life be confined to analogs of Earth. Instead, scientists would focus on the diversity of life-supporting conditions, pushing the boundaries of our imagination and our understanding. This paradigm shift would be more than just academic. It would ignite the curiosity of the public, sparking widespread interest in the unknown. People everywhere would be captivated, their imaginations set aflame by the notion that life could exist in ways and places never before thought possible. Art, culture, and philosophy would likely be influenced by this discovery, prompting deeper reflections on humanity's place within the vast cosmic tapestry. As such a discovery unfolds, it would undoubtedly become a top priority for space missions. Probes and eventually crewed missions would be dispatched to study these oceanic worlds up close. The goals would be clear: sample the planet's waters, map its deep oceans, and search for signs of life. The technological hurdles to such an exploration would be immense, pushing the boundaries of current technologies. The development of advanced robotics, new submarine technology, and life support systems would be crucial in conducting research in these extreme environments. This could lead to an era of unprecedented technological innovation as we learn to navigate and understand alien worlds. Moreover, the prospect of life forms based on elements other than carbon would offer a tantalizing mystery for scientists. For centuries, carbon has been considered the backbone of life due to its unique ability to form stable, complex molecules at the temperatures and pressures typical of Earth. Yet, as we explore the cosmos, we must ask, could life thrive using a different biochemistry? The vastness of the universe suggests that alternative pathways for life might be possible under the right conditions. Silicon is frequently proposed as a potential alternative to carbon for the basis of life. Like carbon, silicon can form 4 bonds, making it capable of creating a wide variety of complex molecules. However, the conditions required for silicon-based life would likely be very different from those on Earth. Such life forms might be found on planets with extremely high temperatures, where silicon compounds could remain stable and reactive. Volcanically active worlds where the intense heat provides the energy necessary for chemical reactions might be prime candidates for harboring such life forms. Another fascinating possibility is the notion of life forms that use ammonia as a solvent instead of water. Ammonia has properties that could support biochemistry at much lower temperatures than water, which opens up the possibility of life thriving in the icy realms of the outer solar system. Moons and dwarf planets, with their frozen surfaces, might host organisms capable of surviving in these cold, distant environments. While these ideas stretch the limits of our current understanding of biology, they encourage us to think beyond Earth's narrow confines, embracing the idea that life could exist in forms radically different from what we know. This expanded view of life challenges the assumptions we've long held about biology. The search for life in the universe has been dominated by the principle of follow the water, driven by the belief that water is essential for life. But as we discover new possibilities for life in extreme environments, it's clear that our search must evolve. The potential discovery of non-carbon-based life would revolutionize biology, challenging our understanding of the very principles that govern life's existence. It would redefine the conditions we consider necessary for life to emerge and remind us of the incredible diversity of the universe. Evolution, under the right circumstances, could take countless forms that are as yet unimaginable. For now, this search remains one of the most captivating frontiers in science, sitting at the intersection of biology, chemistry, and astronomy. As we continue to push the limits of our knowledge, we must remain open-minded to the possibility that life may exist in ways we cannot yet fathom. In doing so, we expand our understanding of the cosmos and the remarkable potential for life in all its infinite forms. Yet, the story does not end with the search for alien life. Imagine the dramatic event of a rogue planet, an object with the mass of a planet yet not bound to any star, entering our solar system. Such an occurrence would send shockwaves through the scientific community. A rogue planet traveling through interstellar space offers a unique opportunity to study a planetary body that has evolved without the gravitational influence of a star. It would be a window into the conditions that prevail in deep space, offering insights into planetary formation, the diversity of planetary objects, and the dynamics of interstellar space. Astronomers would be quick to deploy every tool at their disposal to observe this rogue planet, from telescopes that analyze its composition and atmosphere to probes that might assess any moons or rings it carries. The path of the rogue planet would be a topic of intense scrutiny, however, especially concerning its gravitational influence. If its trajectory brought it near any of the planets in our solar system, the effects could be profound. The gravitational pull could alter the orbits of nearby planets and even disturb the paths of asteroids and comets. This could lead to a dramatic increase in cosmic activity as objects are jostled from their usual orbits. In a worst-case scenario, if the rogue planet passed too close to Earth, the gravitational disturbance could be catastrophic, causing significant changes to our planet's orbit or even triggering an impact. While such an event would be unlikely, the long-term effects of a rogue planet's passage would still present a potential threat. The stability of the solar system could be disrupted, forcing us to reconsider the fragility of the cosmic balance we often take for granted. The arrival of such an object would forever alter our understanding of the universe's complexity. It would underscore the delicate nature of our place in the vastness of space, reminding us that the stability we often assume is not guaranteed. For scientists, the rogue planet would represent an extraordinary opportunity to deepen our understanding of planetary dynamics and the forces at work in the universe. The consequences of its passage, however, would serve as a reminder of the unpredictable and often chaotic nature of the cosmos. But widespread changes over time, the stability of the asteroid belt, Kuiper belt, and Oort cloud could be compromised. This shift in dynamics would significantly increase the likelihood of asteroids being directed towards the inner solar system. Such a threat, particularly from a rogue planet, would demand a coordinated global effort to track and study its potential path. The collaborative nature of this response would likely involve scientists, astronomers, and governments working together to assess the risks and develop contingency plans to protect Earth from potential impacts or other hazardous outcomes. In a broader context, an encounter with a rogue planet would serve as a powerful reminder of the universe's dynamic and unpredictable nature. This scenario could ignite conversations about planetary defense and the urgent need for enhanced space surveillance. Such discussions could help us prepare for future astronomical threats and better understand the cosmic forces at play. Although the concept of a rogue planet entering our solar system remains hypothetical, it highlights the necessity for continued vigilance and scientific exploration. It underscores humanity's role in safeguarding our place within the ever-evolving cosmos. Now, imagine the confirmation of a signal from intelligent aliens. This would be a watershed moment in human history, irrevocably altering how we perceive our place in the universe. The range of human reactions would likely be vast, shaped by individual beliefs, cultural backgrounds, and societal norms. Initial responses could span from exhilaration and awe at the realization that we are not alone in the cosmos, to fear and apprehension regarding the intentions of such extraterrestrial beings. Public interest in space and science would undoubtedly surge, sparking widespread support for further space exploration and research aimed at understanding and communicating with these newfound intelligences. In this new age of cosmic discovery, governments and international organizations would find themselves at the heart of the response, orchestrating a global effort to decipher the alien message and formulate a reply. This monumental task would likely involve scientists, linguists, and experts from various disciplines, underscoring the importance of interdisciplinary collaboration when faced with challenges of cosmic scale. Yet, alongside the excitement, the discovery would provoke deep philosophical and existential questions, challenging humanity's long-held beliefs about spirituality, our place in the universe, and the nature of intelligence itself. Religions, philosophies, and ideologies would face the daunting task of integrating this new understanding into their teachings and worldviews. Would humanity's faith traditions embrace this revelation, or would they view it as a challenge to existing doctrines? Furthermore, the confirmation of extraterrestrial intelligence could spark security concerns, particularly regarding the risks of revealing our presence to a technologically advanced civilization. This could open the door to debates about whether we should respond to the signal or whether such communication could place humanity in danger. The cultural and media landscape would undoubtedly be transformed by this revelation. Movies, books, and art would reflect humanity's evolving relationship with the idea of extraterrestrial life. Social media platforms would buzz with speculation, opinions, and perhaps misinformation, underscoring the need for responsible communication and education. The confirmation of alien intelligence would ignite both wonder and fear, curiosity and caution. Humanity's reaction to such an event would define an era, one that could either bring us closer together or further divide us. In the aftermath of such an event, the world would likely undergo a period of profound reevaluation. As we confront the mystery of life beyond Earth, we would be forced to reconsider what it means to be human. What is our place in this vast, mysterious expanse of the cosmos? How do we define intelligence and life itself? The discovery of extraterrestrial intelligence would mark a monumental shift in human consciousness, forever changing the course of history. Should Earth's orbit drastically shift, the consequences would be nothing short of catastrophic. The first and most pressing impact would be on the climate. A move closer to the sun could result in scorching heat waves, potentially drying up oceans and rendering vast parts of the planet uninhabitable. Conversely, if Earth were to drift farther from the sun, a deep freeze could descend upon the planet, threatening the survival of countless species. Seasons, as we know them, might cease to exist, throwing ecosystems and agriculture into chaos. These environmental disruptions would have far-reaching consequences, affecting everything from food production to biodiversity. The altered gravitational pull between Earth and the Moon would also bring about significant changes. Ocean tides could become unpredictable, leading to extreme weather patterns and tidal events that would further challenge humanity's ability to adapt. In addition to these environmental concerns, human health could be put at risk. Increased exposure to solar radiation, along with potential vitamin D deficiencies in a colder or dimmer world, could lead to widespread health crises. A drastic change in Earth's orbit would disturb the delicate balance that sustains life, pushing our planet and all of its inhabitants into a new and uncertain era. Finally, while the likelihood of a rogue black hole passing near our solar system remains extraordinarily low, the potential consequences would be catastrophic should it occur. The gravitational forces at play in such an event would likely disrupt planetary orbits, potentially causing chaos within the solar system. The idea of a black hole's influence on our celestial neighborhood is a reminder of the vast, unpredictable forces that shape our existence. In conclusion, whether from a rogue planet, an alien signal, or a shift in Earth's orbit, humanity's response to cosmic events will define our future. These events highlight the fragile, dynamic nature of our place in the universe and underscore the importance of science, cooperation, and preparedness in safeguarding our future. But not entirely impossible. Space is vast and sparsely populated, making such an event extremely unlikely. Black holes, particularly the supermassive ones that reside at the centers of galaxies, are usually stationary, held in place by the immense gravitational pull of the galaxy's mass. However, smaller black holes, the remnants of massive stars that have collapsed into themselves, could potentially drift through space. These wandering black holes would travel slowly, but if one were to venture close enough to our solar system, its gravitational influence could throw our planetary system into chaos. Imagine the consequences. The orbits of planets, comets, and asteroids could be disrupted, some objects flung out of the solar system, while others might be sent on a collision course with the Sun or even Earth. The perturbation might extend into the Oort cloud, a vast sphere of icy bodies on the outskirts of our solar system, increasing the chances of comets entering the inner solar system. This could pose a significant threat to Earth. Although the sheer distances between objects in space make such a scenario highly improbable, the thought of a wandering black hole passing near our solar system remains a captivating, albeit unlikely, possibility. Shifting gears to an entirely different yet equally ambitious notion, harnessing energy directly from a star, especially our sun, could revolutionize how humanity powers its civilization, marking a monumental leap into an era of energy abundance. Imagine tapping into the sun's vast power on a scale far beyond our current solar panel capabilities. This concept, often visualized as a Dyson sphere, involves surrounding a star with an enormous array of energy collectors, designed to capture a substantial portion of its energy output. The energy harvested could fulfill the needs of the entire planet many times over, potentially providing a near-limitless supply of clean energy. Such a breakthrough could signal the end of our reliance on fossil fuels, significantly reducing greenhouse gas emissions and helping to mitigate climate change. Furthermore, this boundless energy could fuel technological advancements that are currently unimaginable. Space exploration would reach new frontiers, and humanity could sustain its growing population while maintaining a high standard of living. However, the construction of such a colossal structure faces immense engineering challenges. To build a Dyson sphere, we would need materials and technologies far beyond what is currently available. Despite these monumental obstacles, the pursuit of such a goal could spark innovations in energy generation and space technology, bringing humanity closer to becoming a truly spacefaring civilization. Now let's delve deeper into the limits of constructing a Dyson sphere. This hypothetical megastructure, designed to envelop a star and capture its power, presents a host of theoretical challenges grounded in our current understanding of technology and the laws of physics. For one, the scale of materials required is unimaginable. To encircle a star like the Sun, we would need an enormous quantity of resources far beyond what Earth can provide. This would likely necessitate mining materials from asteroids or even other planets. The structural integrity of such a massive construct would also be a major issue. the sphere would need to endure the intense heat and radiation emitted by the star, as well as the gravitational forces that could tear apart weaker materials. At present, there are no materials capable of withstanding these conditions over such vast expanses. Energy distribution and management within the Dyson sphere present additional complexities. Transmitting the harvested energy back to Earth or to other locations would require technologies capable of efficiently storing and transferring energy across vast interstellar distances, technologies that humanity has yet to develop. Furthermore, constructing such a massive structure around a star could have unpredictable effects on the surrounding stellar system. The gravitational effects of this structure could destabilize the orbits of nearby planets and celestial bodies, potentially leading to unforeseen consequences. In short, while the idea of a Dyson sphere is intriguing, the road to constructing one is filled with extreme engineering, material, and energy challenges. Achieving this dream would require breakthroughs in science and technology that humanity has yet to even begin to fathom. On another cosmic scale, consider the prospect of mapping the entire observable universe. Such a map would be a breathtaking mosaic of cosmic wonders, illustrating the vastness and incredible diversity of the cosmos on an unimaginable scale. This map would showcase an intricate web of galaxies, each one a vast collection of billions of stars spread across the dark expanse of space. These galaxies would be grouped into clusters, and these clusters would combine into superclusters, forming a gigantic cosmic web with enormous voids of seemingly empty space in between. At the largest scale, the observable universe would appear strikingly uniform thanks to the cosmic microwave background radiation, a faint glow left over from the Big Bang. This radiation, visible in every direction, provides a snapshot of the universe when it was only about 380,000 years old. The map would also highlight the filamentary structure of the universe, where galaxies and galaxy clusters align along invisible threads of dark matter, adding yet another layer of mystery and wonder to the cosmos. Thus, the construction of such an expansive map of the universe would not only reveal the structure of the cosmos, but also invite us to delve deeper into the mysteries of dark matter, gravity, and the very origins of existence itself. Because of the finite speed of light, this map becomes more than just a representation of the cosmos. It also serves as a time machine of sorts. The further out we look, the older the light, allowing us to peer back in time to the universe's early stages, nearly approaching the Big Bang itself. However, it's crucial to note that this map only shows the observable universe. Beyond this observable horizon, the universe continues to stretch out, remaining beyond our sight and current understanding. This boundary hints at the vast, unfathomable scale of the cosmos, filled with mysteries that remain hidden from our eyes, inviting both awe and curiosity. The idea that the laws of physics could vary in different parts of the universe is a deeply fascinating and profound possibility. It challenges everything we think we know about the cosmos. Our current understanding of the laws of physics, captured in well-established theories such as quantum mechanics and general relativity, is built on observations and experiments carried out within the bounds of the observable universe. From the behavior of subatomic particles in earthbound colliders to the motion of galaxies billions of light years away, these laws have displayed remarkable consistency across immense distances and varied conditions. But what if, in other regions of the universe, those laws are not the same? Could different areas of space have different physical rules, depending on how symmetry was broken during the formation of the universe? The concept of a multiverse offers one possible explanation. In the multiverse model, different universes could follow entirely distinct sets of physical laws based on the particular conditions in which they formed. String theory, another promising framework, suggests the existence of extra dimensions that could alter our understanding of physics. These dimensions could modify physical laws at different scales or locations, affecting the very fabric of reality itself. Moreover, theories like cosmological natural selection propose that the laws of physics might gradually change over time or space. This evolving framework would imply that physical constants, or the strength of fundamental forces, could vary depending on cosmological distances or even over cosmic timescales. These subtle shifts might go unnoticed in our local universe, but could have a profound impact on larger, more distant realms of space. The ability to observe deeper into space and further back in time is constrained by several significant factors. Chief among these challenges is the finite speed of light. Since light travels at a constant speed, we can only see as far back as the light that has had time to reach us. This means the observable universe has an inherent boundary beyond which light has not had enough time to travel to Earth since the Big Bang. This limitation creates a cosmic horizon, marking the edge of our observable universe. The expanding universe itself also plays a role in limiting our view. As space stretches, it causes the light traveling through it to redshift, a phenomenon in which the wavelength of light is stretched, shifting it towards the red end of the spectrum. At extreme distances, this redshift becomes so severe that the light moves beyond the detectable range of our instruments. This makes it increasingly difficult to observe galaxies and objects located at the farthest reaches of the cosmos. In addition to the physical constraints, technological limitations also play a significant role in our ability to observe distant galaxies. Detecting faint light from these far-off places requires instruments of extraordinary sensitivity and precision. Telescopes like Hubble and the soon-to-be-launched James Webb Space Telescope represent the cutting edge of astronomical technology, but they still have limits in terms of their resolution and the clarity of the images they produce. The Earth's atmosphere complicates the situation even further. Atmospheric turbulence can blur the images of celestial objects, and certain wavelengths of light are absorbed before they can even reach the surface. This is why many observatories are situated at high altitudes or rely on space-based telescopes. Our theoretical models also constrain our understanding of the cosmos. As we peer back in time, we approach eras like the cosmic dark ages and the Big Bang, epochs where our current understanding of physics becomes murkier. Exploring these ancient realms might require entirely new theories or adaptations of our existing models to better explain the universe's origins. In terms of interstellar communication, overcoming the vast distances between stars and ensuring clear, undistorted signals is a monumental challenge. Messages sent even at the speed of light can take years, decades, or even centuries to reach their destination. This delay makes real-time communication impossible and necessitates patience for the return of any signal sent into the depths of space. To maintain clarity over such vast distances, one approach is to use highly focused beams of radio radiation, such as lasers, which minimize signal dispersion and increase the likelihood of detection. Another strategy is to utilize frequencies that are less likely to be absorbed or disrupted by cosmic dust and other interstellar mediums. The radio spectrum, specifically the water hole between 1,420 MHz and 1,666 MHz, is considered ideal for long-distance communication. This range of frequencies is relatively quiet, meaning there is less interference, and it can travel vast distances through space with minimal disruption. The development of technology capable of both transmitting and receiving these signals is essential. This includes the creation of highly sensitive receivers, large antennas, and advanced digital signal processing systems that can filter out noise and enhance weak signals from the farthest reaches of the galaxy. Another significant hurdle is encoding messages in a way that could be universally understood. Any communication intended for extraterrestrial intelligence needs to be encoded using universal principles, likely based on mathematics and physics, as these are considered universal languages that any advanced civilization with a scientific understanding could potentially comprehend. These efforts in interstellar communication, when combined with international cooperation and sustained investment in scientific research, represent our best hope of reaching across the stars. As our understanding of the universe deepens and our technological capabilities grow, we may one day find ourselves in contact with intelligent life beyond our world. The farthest reaches of the universe may also hold the key to materials and elements that stretch the boundaries of our scientific understanding. On distant planets and moons, conditions unlike those on Earth might give rise to new forms of matter or unknown elements. Carbon, for instance, could crystallize into diamond-like structures under the extreme pressures and temperatures of a supermassive planet, creating novel forms that could revolutionize our understanding of chemistry. Similarly, within the dense cores of neutron stars, matter exists in a state known as neutron degenerate matter, where atomic structures collapse under intense gravitational pressure, potentially forming neutronium, a material unlike anything we know on Earth. The search for unknown elements does not stop here. Some theoretical physicists suggest the existence of islands of stability in the uncharted regions of the periodic table, where super-heavy elements might exist with relatively long half-lives. If discovered, these elements could exhibit entirely new chemical and physical properties, offering vast potential for new technologies and materials. Exploring these possibilities would push the limits of human ingenuity, driving us to develop new tools and theories to uncover the secrets of the universe's most distant corners. Humanity's capacity to explore space, however, is constrained by a combination of technological, physiological, and financial challenges. But as our understanding deepens and our technology advances, the stars will become closer, and the mysteries of the universe will slowly reveal themselves. But it is expanding rapidly with advancements in science and engineering, opening new possibilities for space exploration. Yet our current direct exploration capabilities are still limited to unmanned probes that have visited every planet in our solar system, rovers on Mars, and a variety of orbiting telescopes that peer deeper into the universe. While manned missions have reached the moon, plans for Mars are still in the drawing stages. The question is, how do we push beyond these initial forays into the great expanse of space? The answer, however, is not simple. The vastness of space itself presents daunting challenges. The nearest star system to us, Alpha Centauri, lies over 4 light-years away. At our current propulsion speeds, reaching it would take tens of thousands of years. Interstellar travel, then, remains a distant dream, one that demands breakthroughs in propulsion methods that we have yet to achieve. Ideas like nuclear pulse propulsion, antimatter engines, and even theoretical concepts like warp drives and wormholes may offer paths to drastically reduce travel times, but these remain firmly in the realm of speculative science. The human body, as resilient as it is not well suited for prolonged space travel. Muscle atrophy, bone density loss, and constant exposure to cosmic radiation all present significant hurdles. To make long-duration missions feasible, we must innovate in areas like artificial gravity, advanced life support systems, and protective shielding. These are not just scientific challenges, they are human challenges that demand immediate attention. Financially, space exploration requires immense investment. For broader exploration to be viable, we need more than just funding, we need international cooperation. Pooling resources and sharing the rewards of discovery could form the foundation for more ambitious space missions. Economic models like space tourism, asteroid mining, and in-situ resource utilization on the Moon and Mars could, in the future, help underwrite these missions. As technology advances, humanity's footprint in space will inevitably grow. The scope of what is feasible could expand exponentially, especially if propulsion technologies, life support, and sustainable living methods in space evolve rapidly. But this potential can only be realized if we remain committed to the dream of exploring the unknown. At the core of our exploration limitations is propulsion technology. The chemical rockets we currently rely on are sufficient for launching spacecraft from Earth's atmosphere, but they are ill-suited for long-duration interplanetary travel. These rockets burn vast amounts of fuel, which increases both the mass and cost of space missions. Fortunately, more efficient propulsion systems like ion drives, nuclear thermal propulsion, and electric propulsion are being developed, but they are still in the early stages and have yet to prove their effectiveness for deep space missions. Equally daunting is the challenge of sustaining human life for extended periods in space. Space is a hostile environment, with dangers such as exposure to cosmic and solar radiation, the effects of microgravity on the body, including muscle atrophy and bone density loss, and the psychological strains of isolation and confinement. While we've developed life support systems for the International Space Station, these systems still depend on Earth-based resupplies and are far from self-sustaining. To sustain long-duration missions, we need closed-loop systems that can recycle water, air, and food, reducing our reliance on Earth. Communication also becomes an increasingly complex issue the farther we venture into space. A signal from Mars, for example, can take up to 22 minutes to reach Earth, making real-time control of rovers and, eventually, the management of crewed missions incredibly difficult. This communication delay adds another layer of complexity to space exploration that must be overcome. Furthermore, there is the ever-present challenge of funding. Space missions are costly endeavors, requiring substantial investments in research, technology development, and infrastructure. While the commercial space industry is growing, lowering costs and expanding access to space, more investment and international collaboration are still required to make broader exploration possible. As technology continues to advance, these constraints will gradually lessen. But in the meantime, financial support will remain a key barrier to further exploration. Another limitation is our limited understanding of space itself. For instance, we are still uncovering the long-term effects of space weather and cosmic radiation on both technology and human biology. As we venture deeper into space, we will undoubtedly encounter unforeseen challenges, requiring adaptive technologies that can withstand a wide range of space conditions. As we address these issues, we'll need to build systems that are robust and flexible enough to respond to whatever the cosmos throws our way. Despite these limitations, there is hope. Ongoing research and development in space science and technology continue to push the boundaries of what is possible. Breakthroughs in propulsion, life support systems, materials science, and robotics are laying the groundwork for a new era of space exploration. As these advancements continue, the day will come when humanity can not only explore the moon and Mars, but venture far beyond into the stars. And now it's important to remember the uncertainty principle, a fundamental concept in quantum mechanics introduced by Werner Heisenberg in the 1920s. This principle states that it is impossible to know both the exact position and the exact momentum of a particle with absolute precision. The more accurately we know one value, the less accurately we can know the other. At first, this might seem unrelated to space exploration, but it offers an intriguing perspective on the unknowns we face. As we push the boundaries of space exploration, there will always be uncertainty. But like the uncertainty principle itself, the more we learn, the more we open up new realms of possibility. The limits of space exploration are not bound by physics alone. They are limited only by our imagination, our resolve, and our commitment to venturing into the unknown. But it has profound implications for our understanding of the universe and the precision with which we can measure cosmic phenomena. In the vast and mysterious realm of space and astrophysics, the uncertainty principle does more than merely limit the tools of our scientific inquiry. It reshapes the very nature of how we perceive reality at its most fundamental level. When scientists peer into the night sky, capturing photons emitted billions of years ago by distant stars, or analyzing the faint whisper of the cosmic microwave background radiation, they are not merely observing objects, they are interacting with a quantum imprint of ancient cosmic events. Each particle of light they measure is part of a quantum tapestry, a signal blurred by the intrinsic indeterminacy encoded in the laws of nature. The uncertainty principle, formulated in the early 20th century by Werner Heisenberg, reminds us that at the smallest scales of reality, precision is not absolute. We cannot know both the position and momentum of a particle with arbitrary accuracy. And when that principle is extrapolated to the cosmic scale, the implications become staggering. Take, for instance, the behavior of matter and energy in the vicinity of black holes. These objects, where gravity crushes matter into a singularity, stand as monuments to the fusion of quantum mechanics and general relativity. Observations of high-energy particles dancing around event horizons or evaporating via Hawking radiation are fundamentally limited by quantum uncertainties. Yet, despite these limitations, or perhaps because of them, we gain a richer, albeit more probabilistic, picture of the universe. The detection of gravitational waves, a triumph of modern physics, offers another breathtaking intersection of quantum limits and cosmic observation. The colossal LIGO and Virgo interferometers must detect distortions in spacetime thousands of times smaller than a proton's diameter. To accomplish this, they rely on lasers and mirrors so finely tuned that quantum fluctuations, like the jittery dance of photons, become significant noise. Quantum squeezing techniques, developed precisely to manage these uncertainties, are now used to push the boundaries of detection, transforming quantum noise from a hindrance into a controlled variable. But the uncertainty principle is not just an obstacle, it is a portal. It tells us that in the fraction of a second after the Big Bang, quantum fluctuations roiled the fabric of space-time, sowing the seeds for all galaxies and clusters we observe today. During the epoch of cosmic inflation, these minute variations were stretched to astronomical scales. The fingerprints of those fluctuations are etched into the microwave background, a relic radiation map of the infant universe. Scientists decipher this map like ancient script, uncovering secrets about the nature of time, space, and everything in between. Even as we marvel at these insights, the same principle that expands our horizons also defines the borders of what can be known. We can map, but not define with absolute certainty. We can detect, but never observe without altering the very thing we study. It is a paradox as poetic as it is physical. And yet, humanity does not retreat from this cosmic ambiguity. We innovate, we adapt, we build better detectors, refine our algorithms, and construct new models of understanding. Our journey into the quantum cosmological frontier continues, undeterred by uncertainty, perhaps even fueled by it. But there are other frontiers, closer to home, yet equally daunting. Among them, the challenge of protecting the human body from the relentless onslaught of cosmic radiation. In the grand theater of space exploration, the unseen hazard of high-energy particles represents a silent, pervasive threat to human health and mission success. Cosmic radiation is not a single entity, but a complex cocktail of charged particles, gamma rays, and X-rays, originating from both within and beyond our galaxy. Protons, helium nuclei, and heavier ions hurtle through space at near-light speeds. On Earth, we are shielded by the thick embrace of our atmosphere and the magnetic cocoon of the magnetosphere. In deep space, that protection vanishes. Astronauts are exposed, vulnerable, and in need of every technological advantage we can muster. Over time, this exposure can have profound biological effects. The most alarming is the heightened risk of cancer. Radiation damages DNA in multiple ways, by directly cleaving molecular bonds or indirectly creating reactive radicals that wreak havoc within cells. Mutations accumulate, some are benign, others begin a cascade toward malignancy. Yet cancer is not the only threat. Radiation penetrates deep into bodily tissues, affecting the cardiovascular system, degrading vessel walls, and altering cellular structures. Over long durations, this can lead to heart disease, a silent killer even on Earth, but with amplified stakes in space. The eyes, too, are not immune. Cataracts, which cloud vision and impair performance, can be induced by radiation exposure. For astronauts tasked with critical operations, such impairment could spell disaster. The central nervous system, perhaps the most vital system for mission success, also lies in the crosshairs. Animal studies suggest that high-energy particles can damage neurons, leading to reduced cognitive capacity, impaired motor skills, and behavioral alterations. In the isolated, high-stress environment of space, even subtle neurobehavioral effects could prove catastrophic. Reproductive health also enters the equation. Though less studied, preliminary data suggest potential harm to fertility and risks to offspring. The long-term genetic impacts of deep space travel may not be fully known for generations. To counter these threats, space agencies deploy a mosaic of mitigation strategies. Shielding is the first line of defense. Spacecraft walls made of aluminum, polyethylene, and hydrogen-rich compounds absorb or deflect radiation to varying degrees. Polyethylene, due to its hydrogen content, is particularly effective against charged particles. Researchers are developing new composite materials that offer improved protection without sacrificing weight efficiency, a critical factor in space travel. Beyond passive shielding, active defense systems are in the works. Concepts for magnetic or plasma fields that replicate Earth's protective magnetosphere are gaining traction. These systems could deflect incoming particles before they even strike the spacecraft. Within the craft, every aspect of design is scrutinized. Sleeping quarters and control modules are often placed in radiation-shielded cores. Mission planners also carefully time launches to avoid solar maximum periods when radiation levels spike. Routes are optimized to minimize time spent in high radiation zones, such as the Van Allen belts. Physiological countermeasures are equally critical. Astronauts engage in daily exercise regimens to combat the effects of microgravity, which amplifies the damage of radiation by weakening muscles and bones. Strengthened bodies are more resilient, both physically and metabolically. And then there is the mind. Isolation, confinement, and sensory deprivation are as dangerous as any cosmic particle. Crews are selected not only for their skills, but for psychological endurance. They train in simulations designed to mimic the isolation of Mars. They learn conflict resolution, stress management, and techniques to sustain morale. Real-time communication with Earth, video calls with family, and the introduction of virtual reality environments provide crucial psychological support. Meanwhile, the threat of high-velocity collisions with micrometeoroids and orbital debris looms large. To mitigate this, spacecraft are armored with multi-layered Whipple shields. When a small object strikes, the outer layer vaporizes it, spreading the energy across subsequent layers and minimizing penetration. These engineering marvels stand as silent sentinels against the violence of the void. This multi-pronged strategy reflects the complexity of the environment astronauts face beyond Earth's orbit. Every risk demands a layered response. Every hazard invites innovation. As our ambitions grow toward lunar bases, Martian colonies, and interplanetary missions, so too must our defenses. And at the heart of it all remains the interplay of uncertainty. In the smallest particles and the largest structures, in the measurement of waves from across the universe, and in the protection of fragile human bodies, uncertainty reigns. But rather than deter us, it challenges us. It fuels our pursuit. It pushes us to build better instruments, develop smarter protections, and think deeper about our place in a cosmos that reveals its truths only in glimmers. In this relentless march forward, humanity does not merely explore space. We reshape our very understanding of existence, guided by the principle that though we may never know everything, we can always know more. And in that pursuit, the uncertain becomes the frontier of the possible, but exerts gravitational effects on visible matter. This peculiar force, silent and unseen, creates a profound riddle at the heart of astrophysics: dark matter. It pulls at galaxies, bends the paths of light, and sculpts the universe's vast structure. Yet it remains forever cloaked in shadows. We do not see it. We do not touch it. Still, we know it must be there, lurking behind the veil of the visible cosmos. The very fact that dark matter interacts gravitationally but not electromagnetically renders it nearly impossible to observe directly. Its presence is inferred, never witnessed. This inferential method, though profoundly insightful, introduces layers of complexity. Scientists track the motion of stars as they spin in galaxies and examine how beams of light curve while passing distant clusters, a phenomenon called gravitational lensing. In these distortions, they glimpse the fingerprints of dark matter. Yet, these clues are indirect, elusive, and scattered, making the task of mapping dark matter akin to drawing the shape of the wind by watching leaves flutter in its wake. Astronomers are not simply contending with something invisible. They are confronting the architecture of the cosmos itself. The universe stretches across unimaginable distances, and within it lies a colossal, ethereal scaffold composed of dark matter, the cosmic web. This web binds galaxies into clusters, clusters into superclusters, threading the cosmos in immense, ghostly filaments. Mapping such a structure is not a task of hours or even years. It is a generational endeavor. To chart the shape of this invisible web, astronomers deploy their most powerful tools across the depths of space. Telescopes such as the Vera C. Rubin Observatory scan the night sky with sweeping precision, set to image billions of galaxies, and trace how their movements hint at the gravitational presence of dark matter. The European Space Agency's Euclid spacecraft joins its effort from orbit, mapping the geometry of the dark universe with unrivaled depth. These are epic undertakings, consuming vast computational resources, immense data sets, and countless hours of analytical labor. And yet, even with these titanic efforts, we only begin to scratch the surface. The observable universe is simply too vast. Even our most ambitious surveys chart but fragments of the whole. The challenge is further deepened by the uncertain identity of the very thing we seek to map. The dominant cosmological model, the lambda cold dark matter model, proposes that dark matter is composed of slow-moving, non-interacting particles. But this is a model built upon assumptions. Other hypotheses abound. warm dark matter, fuzzy dark matter, even entirely different formulations of gravity. Could we be mistaken in thinking dark matter exists at all? Some physicists suggest modifications to gravity itself might account for the observed anomalies. Laws of physics that work perfectly on Earth might twist and evolve under the vastness of the cosmos. In this debate, the universe offers no easy answers. Distinguishing between these competing explanations requires the kind of precision that stretches the limits of our current technology. It demands the development of new methods, better detectors, and models that can account for the vast diversity of structures observed in space. It also demands patience. Every refinement of our instruments, every new algorithm applied to cosmic data is a step forward. Piece by piece, the hidden architecture of the universe begins to emerge. Despite the towering challenges, progress is being made. As we improve our ability to filter noise, interpret lensing effects, and model gravitational behavior, the contours of the dark universe become more tangible. Advanced simulation techniques, combined with AI-powered data analysis, are beginning to reveal not just where dark matter might lie, but how it behaves, how it flows, and how it shapes the galaxies and voids that fill the observable sky. But even as we probe the depths of space, we must remain vigilant, for the cosmos has a history of surprises. Preparing for the unknown in space exploration is not merely an engineering question. It is a philosophical stance, a commitment to flexibility, a recognition that the greatest discoveries often come uninvited. Space is a canvas of unpredictability, from volcanic eruptions on alien moons to subsurface oceans, from unexpected radiation belts to entirely new chemical compounds. The history of exploration beyond Earth is riddled with the unforeseen. Mission planners today must therefore build not only for certainty, but for surprise. Every mission must be equipped with contingencies. Plans must be adaptable. Instruments must be versatile. Software must be updatable. Consider how modern spacecraft are built. They are no longer designed solely to perform a fixed set of tasks. They are engineered with the capacity to evolve. Mid-mission software updates, reprogrammed objectives, even autonomous rerouting are now standard capabilities. When the New Horizons probe flew past Pluto, it captured data no one had expected. Vast nitrogen glaciers, towering ice mountains, and a pink haze of atmospheric particles. The mission's success was not just in its design, but in the readiness of its team to embrace the unexpected. That readiness is forged through interdisciplinary collaboration. Missions now bring together experts in planetary geology, astrobiology, physics, chemistry, and artificial intelligence. Each brings a unique lens to the unknown. A planetary scientist sees terrain where others see noise. An atmospheric chemist reads life signs in spectral lines. A roboticist ensures the instruments remain steady on alien ground. This blend of expertise ensures that when the unknown arrives, as it inevitably will, the team is ready not just to react, but to understand. Technology also leads the charge. Instruments today can see farther, detect fainter signals, and operate with unprecedented precision. Spectrometers read the elemental composition of distant atmospheres. Infrared telescopes peer through dust to glimpse star formation in its earliest stages. Machine learning algorithms sift through torrents of data to find patterns even human eyes cannot detect. Autonomous systems onboard spacecraft are being trained to make decisions in real time, an absolute necessity when communications with Earth take minutes or even hours to arrive. And behind every mission is a human story. Astronauts and mission controllers undergo extensive training. They rehearse emergencies. They simulate the unthinkable. They drill responses to engine failures, system glitches, and environmental hazards. But they also train to respond to wonder, to the strange signal, the odd crater, the plume where none should be. These men and women are not just operators of machines. They are explorers in the truest sense, equipped to navigate not just space, but the unknown. Just as crucial as hardware and training is the culture within space agencies and research institutions, a culture of curiosity, a willingness to follow the unexpected lead, even if it threatens to derail original objectives. Some of the most profound discoveries in space science have come when missions dared to veer from their course, when planners prioritized inquiry over rigidity. Serendipity is not an accident. It is the reward of those prepared to see beyond their initial expectations. The discovery of exoplanets, the detection of cosmic microwave background radiation, the evidence of subsurface oceans, all arose from minds and missions open to surprise. And so as we chart dark matter's ghostly map and journey deeper into the abyss of space, we must embrace uncertainty not as a weakness, but as a frontier. What lies beyond the known edges of the map? What secrets still await discovery in the dark valleys between the stars? Are we truly alone, or does the cosmic silence conceal life beyond comprehension? The story of the universe is still being written. Its pages stretch far beyond the limits of our sight. But with each mission launched, each telescope aimed skyward, each calculation refined in the quiet halls of research labs, we come closer to understanding our place in it. Now, as we pause to look back across the grand sweep of the cosmos, we ask you, what do you believe is out there? What mysteries will the next generation uncover? Let us know your thoughts. The universe is listening.